Hi everyone, welcome to goclasses. So let's start this session. In this lecture, we will solve some questions. Then we will study closure properties of RE languages, recursive enumerable languages, and recursive languages. REC means recursive. Okay. So closure properties of RE and REC languages that we will study. And also we will study one very important theorem. Okay. One very important theorem that we will study. Okay. So now let's start this. So let's do some recap through questions. Okay, so we are going to solve some questions, and these things you already know, right? That recursive enumerable languages, these are also called type 0 languages, because for RE languages there is a you have type 0 grammar. Okay, so RE languages, for RE languages we have type 0 grammar. So that is the reason I can say RE languages are also called type 0 languages. These context sensitive languages, CSL, these are also called type 1 languages. Context free languages are also called type 2 languages, because type 2 grammar means context free grammar. So for context free languages we have context free grammar. Context free grammar is also called type 0 type 2 grammar. So next, regular languages are also called type 3 languages, because regular grammar is also called type 3 grammar. Okay, so these things you already know. You know the definition of recursive enumerable language. What is the definition of RE language? And what is the definition of recursive language? So that you already know. You know that what is the definition of RE language? Tell me, what is the definition of RE language? What is the definition of RE language? What is the definition of RE language? That is basically a language is RE. I can say language L is RE. When can I say language L is RE? Tell me. When can I say language L is RE? If and only if there exists a Turing machine. Okay, if and only if there exists a Turing machine. There exists a Turing machine. It is accepted by some Turing machine. So there exists a Turing machine M for L. Okay, there exists a Turing machine M such that M accepts L. Okay, such that LM is equal to L. Okay, such that M accepts L. So I can say M accepts L. M accepts L. Okay, and you know this is the definition of RE language. And tell me one thing. So if you have Turing machine, then what I can say? Then what should happen? If you have a Turing machine M, then what should happen? If you have a Turing machine M, then what should happen? Then for the strings in the language, basically for the members, what should happen? It should definitely halt and accept. It should definitely halt and accept. It should definitely halt and accept. And for the remaining, we don't care. For the remaining, we don't care. Yes or no? If you have a Turing machine M for L, then if you have a string which is not in L, if you have a string which is not in L, means these are the known members. Means these are the known members. Okay. So if you have a string not in L, then we really don't care. Okay. Then we really don't care. We don't care what happens. We don't care what happens. Okay. We don't care if it halt and reject. If it halt and reject, we don't care. Okay. If it halt and reject, or it can never halt, or it may go to infinite loop. Okay. Or it may never halt. So basically, if you have a language, when can I say a language is RE? A language is RE if there exists a Turing machine which accepts L. There exists a Turing machine which will accept L. Accepting L, that means what? Turing machine is accepting language. That means what? That means that for members of this language L, it will halt and accept. And for non-members, the strings which are not in L, for those Turing machine may halt and reject. Okay, either it may halt and reject, or it may loop. Either it may halt and reject, either it may halt and reject, or it may loop. Okay, so either it will do this or do this. This is the definition of RE language. What is the definition of REC language? What is the definition of recursive language? REC means recursive. REC means recursive. Recursive means decidable, or you can call it decidable. Decidable language. So what is the definition of that? That means there exists a decider. There exists a halting Turing machine. There exists a halting Turing machine M, or you can say there exists a decider. Correct? So you can say there exists a halting Turing machine which will always halt on all the strings. So there exists a halting Turing machine. There is at least one halting Turing machine. Okay, there exists a halting Turing machine such that M will accept L. Now this halting Turing machine M. So what should happen? This halting Turing machine M. So what it should do? Because this is halting Turing machine M. This is halting Turing machine M. So what it should do? If you give the okay, on members of L, on members of L, it will halt and accept. It will halt and accept. On members of L, it will halt and accept. On non-members of L, it will halt and reject. But because this is a halting Turing machine, so this will always halt. Because this is a halting Turing machine, so it will always halt. It will always halt. Okay, so it will always halt because this is a halting Turing machine. So this is the idea. Now, anyway, this is the definition of RE language. This is the definition of REC language. Very simple. Okay, now tell me, yeah, okay, so this is the complete picture. We already know this is the complete picture, that every regular language is DCFL, every DCFL is a CFL, every CFL is a CSL, every CSL is Turing decidable, means every CSL is recursive, every recursive is RE. Okay, every recursive is RE. And there are some languages which are not RE, and there are some languages which are not RE, like this language L. So I can say this is not RE. There are some languages which are not RE. So this language L, this is not RE. Okay, like the diagonalization language. Very good. The diagonalization language, and also the complement of ATM, the complement of halting problem. Okay, also equivalence of Turing machines. Yes or no, Mavit? Correct. Equivalence of Turing machines. Equivalence of Turing machines that we have already seen. Okay, so anyway, similarly, like emptiness problem of Turing machines, that is also not RE. Okay, so we have seen many not RE languages. Many not RE languages we have seen, like emptiness of Turing machines. Given a Turing machine, is the language empty? Okay, so that is also not RE. Anyway, so this is the idea. Now let's move on. Now let's see some questions. Okay, we are going to some questions. So understand the definitions and solve these questions. Okay, so now tell me the first question. Question number 1. If L is RE language, then how many Turing machines are there which will accept L? Tell me how many Turing machines are there which will accept L? So how many Turing machines we have which accept L? So there are infinitely many Turing machines. You can create infinite number of Turing machines. You can create. So I can say there are infinite number of Turing machines. Okay, infinite number of Turing machines you can create. You can keep creating. Okay, you can keep adding unreachable states. Yes or no? Infinite number of Turing machines you can create. It is like this. For example, tell me. If you, okay, if you have a Turing machine, then you have a program. Okay, then you have a program. So for any problem, for example, let's assume your problem is addition problem. For example, this is your problem. Okay, addition problem, or I can say this is your problem. www. Now whatever problem you have. Okay, for example, a power n, b power n, c power n, d power n, whatever problem you have, how many program you can write? Tell me, how many program you can write? How many programs you can write for any RE language? For any RE language, for any problem, how many programs? Infinitely many program. For example, for addition, if you want to print, okay, if you want to do addition, if you want to do addition of two numbers, if you want to do addition of two numbers, okay, then how many programs you can write? Okay, how many programs you can write? Infinitely many programs you can write. Infinitely many programs you can write. Okay, programs you can write. Just keep adding unnecessary comments, like Yuvraj is saying. Yuvraj is saying that unnecessary comments you keep putting. Okay, yeah, very good. Okay, so infinitely many programs you can write. Keep putting unnecessary statements. Keep putting unnecessary, or I can say keep putting unnecessary comments. Agree? Keep putting unnecessary statements. Unnecessary statements, or I can say comments. So keep putting unnecessary statements, or I can say comments. There is no problem. So you can create infinite number of programs you can create. Similarly, if you have a RE language, then there exists a Turing machine, right? Yes or no? If you have a RE language, it means there exists at least one Turing machine is there. There exists a Turing machine. There exists a Turing machine. Now from this Turing machine, you can create infinite number of Turing machines. Is this clear? There exists a Turing machine. Now from this Turing machine, you can create infinite number of Turing machines. Okay, keep adding in unnecessary states. Keep adding, okay, unreachable states. Unreachable states you can keep adding. Okay, unreachable states. Is this clear? Or what you can do, you can change the alphabet, tape alphabet you can change, keep adding unnecessary tape symbols. Okay, but basically you can do many things. Okay, so anyway, I can say that RE language means there exists a Turing machine. There exists a Turing machine. For this, from this Turing machine, what you can do, you can keep adding unreachable states and you can create infinite number of Turing machines. Okay, let's move on. Tell me about this one. If you have a recursive language, then how many Turing machines are there? For recursive language, how many Turing? Remember, every halting Turing machine is also a Turing machine. You know this. You already know every halting Turing machine is also a Turing machine. Is also a Turing machine, which always halts. Okay, it always halts. It is a Turing machine which always halts. It is a Turing machine which always halts. Okay, it is a Turing machine which always halts. Now, so very simple. Now tell me, so for a recursive language, how many Turing machines are there? Again, infinite number of Turing machines. Again, infinitely many Turing machines you can create because there exists a Turing machine. This is also RE language, right? This is also RE language. This is also RE language. So this is also RE language. So there exists a Turing machine. Now again, you can create infinite number of Turing machines. Now from this again, you can create infinitely many Turing machines you can create. Okay. So this is the idea. Now let's move on. Tell me about this one. If you have a recursive language, how many halting Turing machines you can create? How many halting Turing machines you can create? If you have a recursive language, then there exists a Turing machine. There exists a halting Turing machine. There exists at least one halting Turing machine. Okay, at least one. Then you can add unreachable states. Then you can add unreachable states. Yes or no? If I add unreachable states, will it become non-halting Turing machine? If I add unreachable states, will it become non-halting Turing machine? Will it become? No. If I add unreachable states, it will still remain halting Turing machine. So again, infinitely many halting Turing machines you can create. Infinitely many halting Turing machines you can create. Okay, yes or no? Because it is a REC language, because it is a recursive language, so there exists a halting Turing machine. There exists a halting Turing machine. Now what you can do, you can okay add unnecessary states. Okay, you can basically what you can do, you can add unnecessary unreachable states. You can add unreachable states. So these unreachable states you can add and you can create infinitely many halting Turing machines. Okay. Now tell me about this one. If a language is such that, read the question carefully. This is true false question, is it true or false? If L is a language such that there exists a Turing machine which is accepting L and M may never halt on some strings which are not in L, then can I say L is not RE? Sorry, L is RE. Then can I say L is RE? Tell me. Then can I say L is RE? So for L, you have a Turing machine. You have a Turing machine that is accepting L. So that is enough. That is enough. If L is a language such that there exists a Turing machine that is accepting L, that is enough to call it RE. Yes or no? There is a language. See, there is a language. There is a language. Okay, there is a language for which there is a Turing machine. There is a language. This L is a language, and there is a Turing machine. There is a Turing machine. This is enough to say that this is RE. This is enough to say that L is RE. This is enough. This is enough. This is enough to say that L is RE. Yes or no? This statement is self-contradictory. No, this statement is not self-contradictory. Yuvraj, this statement is not self-contradictory. Statement is correct. Okay. The statement is correct. Statement is not. Statement is correct. Okay. Now is this clear? Tell me. Is this clear now? Tell me, is this question clear? Okay. So you have a language L. L is a language. There is a Turing machine that is accepting L. So because there is a Turing machine, this is enough to call it RE. This is enough to call this language RE. Tell me about this one. Tell me about this one. Think about it. Think about it. Tell me. So what about this statement? L is a language. Again, L is a language. There is a Turing machine M that is accepting L. Okay, there is a Turing machine M that is accepting L. And the question is saying that M may never halt on strings not in L. Then can I say this is not recursive? Then can I say this is not recursive? Okay. So let me ask you a very simple question. Let me ask you a very simple question. Let me give you this language L. L equal to this language. Okay, let's assume this language L you have 0, uh, 0, 1 star, or maybe 0, 1 plus. Okay, so tell me, this language is RE. Can I say this language is recursive? Can I say this language is recursive? Tell me, can I say this language is recursive? This language is recursive, right? This language is recursive because this is regular. Because this language is regular, every regular language is recursive. So this language is RE also. So this language is now. Tell me. For this language, can I create a Turing machine? Can I create a Turing machine? Can I create a Turing machine? Can I create a Turing machine which which never halt on 100? Tell me, can I create a Turing machine which never halt on 100? For this L, can I create a Turing machine which never halt on 100? Which never halt on 100? Can I create this type of Turing machine? Can I create? Of course you can create. Yes, can be created. Can I create a Turing machine? Yes, you can create Turing machine, right? Okay. So remember, if you say that language is recursive, it does not mean every Turing machine is okay. This language, if you say L is recursive, okay, if you say L is recursive, does it mean every Turing machine for L is halting Turing machine? Does it mean every Turing machine of for L is halting Turing machine? Does it mean? Tell me, does it mean? Does it mean that every Turing machine for L is halting Turing machine? No. So what it means? Then what it means? It means there exists a Turing machine which is halting Turing machine. There exists a Turing machine L which is halting Turing machine. There exists a Turing machine for L which is halting Turing machine. Yes or no? Is this clear or not? Tell me. So this is important. Remember, can I say every Turing machine for L is halting Turing machine? If your language is recursive, can I say every Turing machine is halting Turing machine? The answer is no. But I can say that there exists a Turing machine which is halting Turing machine. Now, if you have this information, okay, let's assume you have this information. There is a language L. Okay, for which there is a Turing machine. There is a Turing machine M. Some Turing machine. There is a Turing machine M accepts. Okay, then so okay. Anyway, what I'm saying now, read this. So tell me, can I say L is not recursive? Can I say L is not recursive? If this particular Turing machine, so this statement is what? So this statement is false. Is this clear? This statement is false. Because maybe this Turing machine is not halting, but maybe some other halting Turing machine is there. Agree or not? Tell me. Maybe some other Turing machine is there. Maybe some other halt. Okay, there exists a halting Turing machine. Okay, maybe some other Turing machine for L always halts. Agree or not? We don't know. Did you get it? Please tell me. Is this clear? Maybe some other Turing machine for L always halts. Tell me, is this clear to everyone? This word is very important. There exists a Turing machine which is halting Turing machine. If your language is recursive, then there exists a Turing machine which is halting Turing machine. But it does not mean that every Turing machine is halting Turing machine. So if a particular Turing machine is not halting Turing machine, then we cannot say yes or no. Is this clear to everyone? Anyone has any doubt in this? So if you have a language L, and for this language L, let's assume a Turing machine M of L for L. A Turing machine M for L is not halting Turing machine, is not halting Turing machine, then does it mean that no, okay, does it mean no halting Turing machine? Tell me, does it mean no halting Turing machine for L? Does it mean no halting Turing machine for L? Does it mean no halting Turing machine for L? Okay, so no. Does it mean no halting Turing machine for L? So you can notice, so L may, still may, okay, remember, yes or no? So I can say, L may or may not be REC. L may, or we cannot say anything, yes or no? L may or may not be REC. Agree or not? Tell me, is this clear? Mavit, all your doubts will clear. Tell me, just tell me this question is clear. This particular question is clear. Tell me. This particular question, is this particular question clear? At least 10-20 variations I am taking. Okay, don't worry. Back to back variations will come. So tell me, is this clear to everyone? Anyone has any doubt in this? Tell me. Language L, such that there is a Turing machine which is not halting Turing machine. Does it mean every Turing machine is not halting? Does it mean there is no halting Turing machine? Does it mean? So the answer is no. It does not mean. There may be some other halting Turing machine. Is this clear to everyone? So very simple question. Now tell me about this one. If L is recursive, then can I say every Turing machine is halting Turing machine? If L is recursive, can I say every Turing machine is halting Turing machine? If L is recursive, then can I say every Turing machine is halting Turing machine? Means every Turing machine always halts. So the answer is no. So the answer is no. Yes or no? So this statement is false, I can say. So this statement is false. Is this clear to everyone? Please tell me. So this statement is false. Okay, very simple. You can see this is a standard question. This is from a top university, this question. Okay, you can notice L is a recursive language, and these are the infinite number of Turing machines. These are the Turing machines for L. Okay, remember L is a recursive language, and this is the list of Turing machines for L. Then can I say, does every MI always halt? Can I say, does every MI always halt? So answer is no. But can I guarantee some MI will always halt? Can I guarantee some MI will always halt? Can I guarantee some MI will always halt? Some Turing machine will always halt. So I can guarantee that, I can guarantee that there exists a I. There exists I such that MI always halts. Yes or no? Yes or no? So we can say there exists a I such that MI always halts. There is at least one Turing machine. So this is the question, you can notice. May or maybe not. Maybe not. At least one of them will halt. Okay, at least one Turing machine will always halt. This is the answer. Tell me, did you understand? Now, did you understand very clearly? Tell me. Now I am going to ask you again many questions I will ask you. Now can you give correct answers? Okay, so read the question very carefully and give the answer again very carefully. Is this clear? So let's start the game. Okay, let's start the questions again. So tell me about this one. If L is recursive language, then at least one Turing machine always halts. Then at least one Turing machine always halts. So this is true. This statement is true. Okay, next. Tell me about this one. If L is RE language, then every Turing machine is a non-halting Turing machine. Okay, if L is RE language, then every Turing machine excepting L loops on at least one string. So this statement is false. Why this statement is false? Maybe this RE language does not mean RE but not REC. Yes or no? It may or may not be REC. Yes or no? So this statement is false. Why this statement is false? Because okay, this L may be REC. L may be regular. L may be recursive. Yes or no? L may be regular, L may be recursive. Because L is RE language, so L may be this. So there exists a halting Turing machine. In this situation, we cannot guarantee basically. Basically, this statement is false. Okay, this statement is false. Is this clear? Tell me. Okay, now tell me about this one. What about this question? If the language is RE but not REC, your language is RE but not REC. Now, is there any halting Turing machine? Tell me about this one. Very simple question I am asking. If L is RE but not REC, this L is RE but not REC. This language is RE but not REC. Can halting Turing machine exist? Tell me. Can halting Turing machine exist? If for this L, can halting Turing machine exist? Can a halting Turing machine exist? The answer is no. Can halting Turing machine exist? The answer is no. Basically, can a Turing machine exist? Can a Turing machine exist? Okay, which always halts? Which always halts? Can a Turing machine exist which always halts? Again, the answer is no. Okay, and Turing machine exist. Can I say Turing machine exist? Can I say Turing machine exist? Can I say Turing machine exist? The answer is yes. Is this clear? So if your language is RE but not REC, then can I say every Turing machine, then read this, then can I say every Turing machine accepting L, on at least one input it will never halt. On at least one input it will never halt. Is this statement true or false? Is this statement true or false? Tell me. So this statement is true, right? This statement is true because your language is RE but not REC. Your language is RE but not REC. So every Turing machine that will accept L, it will, for some input, it will never halt. For some input, it will never halt. Okay. That input will be outside of L. That input will be outside of L. So we can say that, what we can say, we can clearly say that. So if your language L is RE but not REC, if your language is RE but not REC, then what will happen? Then whatever Turing machine you create, whatever Turing machine M you create, remember whatever Turing machine M you create, okay, then, okay, whatever Turing machine M you create, then what will happen? There exists a W which is not in L. There exists a W which is not in L. TMM never halt on W. Never halt on W. Okay. Is this clear? For some non-member, it will never halt. Whatever Turing machine you create, for some W, remember, for some W which is not in L, M never halts. Yes or no? M never halts. Okay. So very simple. So these questions. Now tell me. So this is the conclusion. You can notice all these questions are taken from a standard resource. All these questions, they are taken from a standard university. So all these questions we have seen back to back. These are the questions that we have seen. Is this clear? Now tell me, is this clear? Okay, let's see this question. Tell me about the answer. Next question, tell me the answer. If M is a Turing machine, then can I say LM is RE? Definitely, by definition. Then LM is RE? Definitely by definition. Can I say may or may not be? May or may not be. May or may not be. And what about this? This also may or may not. Information is not enough. Yes or no? Information is not enough. Agree or not? Yes or no? So very simple. This will definitely happen. LM is RE. This will definitely happen. But we cannot say anything about recursive. We cannot say anything about recursive. We cannot say anything about RE but not RE. We cannot say anything. So this is another question from the same resource. from the same standard university, the same. Okay, so you can notice if M is Turing machine, then I can say LM is RE. Yes, definitely. Okay, LM is RE definitely. But is it recursive? Enough. We don't have enough information. Is it RE but not REC? We don't have enough information. Okay, let's see more questions. Tell me about this one. Okay, what about this one? M is a Turing machine that halts on all inputs. M is a Turing machine that halts on all inputs. It is halting on all inputs. So M is a Turing machine that is halting on all inputs. Now I can say that this will definitely happen. This will definitely happen. And this will definitely not happen. Never. Agree? All the three things we can say. Yes or no? This will definitely happen. This will definitely happen. And this will never happen. Okay, so you can notice if you have a Turing machine, very simple. If you have a Turing machine which always halts, if you have a Turing machine which always halts, then I can say definitely it will be RE. Okay, which word? Because of which word it is RE? Because of which word it is RE? Because of this word. Because of this word it is RE. Okay, now because of which word this is REC? Because of this word it is REC. Okay, so it can never happen that it is RE but not REC. Okay, now let's see. Let's see about this. What about this one? M is a Turing machine. LM is recursive. Okay, this information is given to you that M is a Turing machine. LM is recursive. Then can I say M always halts? Then can I say M always halts? No. Okay, because remember, for every recursive language, remember, because you know that if L is recursive, then you can easily create a Turing machine which is not halting. Okay, yes or no? We can create a Turing machine M which is not halting Turing machine. Yes or no? We can create a Turing machine M which is not halting Turing machine. Agree or not? Okay, and remember, there exists a halting Turing machine. So we can say there exists a halting Turing machine. Okay, not every Turing machine is halting Turing machine. Not every Turing machine is halting Turing machine. Yes or no? Not every Turing machine for L is halting Turing machine. Clear? So this question, for this question, answer will be no. Is this clear? Okay. Tell me about this one. What about this question? If if M is a Turing machine, LM is RE but not REC. LM is RE but not REC. LM is RE but not REC. Then can I guarantee M is not halting Turing machine? Can I guarantee M? Okay, yes, I can guarantee. So this statement is yes. Okay, because we can guarantee that. Okay, if you're then now in this situation, we can guarantee M is definitely not halting Turing machine. M is definitely not halting Turing machine. Okay, so these are again these are the same question. You can notice. Okay, one by one, all these questions from this standard resource, all the questions I have taken from this standard resource, every question I have taken. Okay, now tell me about this one. M is a Turing machine. M loops on W. M is a Turing machine. M is a Turing machine. M loops forever on a particular string W. On a particular string W. Can I say it is RE? Yes, definitely. Because of this, this is enough. This is enough. This Turing machine is enough. Okay, tell me about REC. Can I say it is never REC? Okay, so can I say it is not REC? Can I say it is not REC? Can I say LM is not REC? Okay, may or may not. May or may not. May or may not. Because okay, because remember, maybe there is some other Turing machine. Maybe. Okay, maybe there exists a halting Turing machine. Maybe there exists a halting Turing machine. Yes or no? So it may or may not be. It may be not REC. It may not be not REC. The same thing. Can I say it is RE but not REC? No. Again, no. Okay, again, may or may not. Again, may or may not. Yes or no? It may or may not. Is this clear? All the questions, back to back, every question. This is also from the same resource. From the same resource, again, the same question. Back, okay, all the things we have seen. Is this clear? All the questions so far. Now tell me, are you confident? Do you have any doubt? At this point of time, do you have any doubt? Whatever we have seen in today's class so far, all the questions, are they crystal clear? Okay, now let's see. So this you already know that Turing machine has many equivalent models. I told you. Okay, Turing machines, they have many equivalent models. I told you that DTM, your Turing machine model, your deterministic Turing machine model, that is equivalent to non-deterministic Turing machine model, that is equivalent to multi-tape Turing machine model, that is equivalent to one-way infinite tape. If you have one-way infinite tape, if you have multi-tape, if you have non-deterministic, okay, if you have multiple heads, multiple tracks, whatever, all these things we have already seen. Okay, all of them we have seen. And this proof also we have seen, yes or no? That NTM is equivalent to DTM. This proof was important. Do you remember this proof? This proof was important. I told you that non-deterministic Turing machine, this is equivalent to deterministic Turing machine. And what was the important thing in this proof? In this proof, what was the most important thing? What we do? We do BFS. Okay, we do okay, for basically we do computation tree. Okay, you have NTM. What we do? The proof is like this. Let's assume you have NTM. Let's assume you have NTM M for L. Let's assume you have NTM non-deterministic Turing machine for L. Okay, then for string W, what you can do? For string W, you can create a computation tree. Yes or no? For string W, there exists. Okay, you can create computation tree. Correct. Yes or no? You can create a computation tree. Now, how can you create DTM? How? Okay, this is your now. How to create DTM? Okay, create now from this you can create DTM. Creating DTM for L. Okay, how to create DTM for L? So what you will do for this computation tree, you will do BFS, not DFS, not DFS. Don't do depth first search. Okay, don't do this. Don't do this, not this. Do BFS. Okay, anyway, this was the idea. Basically, Dove-telling method. Yes, very good. Basically, the Dove-telling method. It was basically the Dove-telling method. It was basically the Dove-telling method. Okay, it was basically the Dove-telling method. Okay, so this was the idea. Now, in the GATE exam, there is no question on this topic. On this, there is no question, but this idea is very important. Okay, someday this question will definitely come. Someday it will definitely come because this is very important. If you study any TOC book, theory of computation book, then this is very important. This proof is very important. Okay, this proof idea, remember, this proof idea is very important. So if they ask you any question from this topic, then they will ask you on this. They will ask you about this, that this is the computation tree. Will you do BFS or DFS? You have a computation tree. Will you do BFS or DFS? So you will do BFS. Basically, Dove-telling method you will apply. Okay, you cannot do DFS. Why you cannot do DFS? Tell me why you cannot do DFS? Because some path can go to infinite loop. Yes or no? Some path can go to infinite loop. Some path. Okay, because you know that in NTM what happens? You know in NTM what happens? If you have a non-deterministic Turing machine M for L, then what will happen? Then you can notice that this will happen on string W. On any string W, you know this. On string W, what will happen? So this will happen that you will start in the start configuration. This is your start configuration. This is your start configuration. So from the start configuration, you can make many moves. Okay, you can make many moves. You can make many moves. You can make. Okay, and so on. So like this, you can create many moves. Now some move can go to infinite. Okay, some path can never halt. Okay, some path may never halt. Some path may halt and reject. Some path it may halt and reject. and some path may halt and accept. Some path may halt and accept. Okay, so this is the idea. Yes or no? Some path may halt and accept, and so on. Now tell me, if you have a string which belongs to L, then what will happen? For this string, what will happen? Tell me. If your string is belonging to L, then what will happen? Then at least one path will halt and accept. In this situation, at least one path will halt and accept. At least one path will definitely halt and accept. In this situation, at least one path in computation tree, at least one path in computation tree, okay, halts and accepts. Okay, at least one path in computation tree halts and accepts. Okay, is this clear? Tell me. And if your W does not belong to L, then what will happen? If your W does not belong to L, if it does not belong to L, then what will happen? If it does not belong to L, then remember, then no path can accept. Then no path can accept. No path can accept. No path can accept. Okay, no path in computer tree can accept. Okay, no path in computation tree accepts. So this can never happen. This can never happen. Every path either it will reject, every path either it will reject or it will loop. Every path either it will reject or it will loop. Either it will loop. Yes or no? Either it will loop or it will halt and reject. Or it will halt and reject. Correct? So these things we have already seen. And how your Turing machine NTM, how Turing machine NTM will reject? How Turing machine NTM will reject? NTM rejects W. How can you say that NTM rejects W? When NTM rejects W, reject. When can I say NTM will reject W? When can I say NTM will reject W? When all path they reject. When all path reject. Yes or no? All path. When all paths halt and reject. When all path halt and reject. All paths halt and reject. So no path can go to loop. 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 Halt and reject. Halt and reject. So every path will halt and reject. All these points we have seen, yes or no? Basically, these are the true false questions. Why I am telling you all these things? Because these are the true false questions. In the exam, they can ask you true false questions. Every point, everything we have already seen. Okay, let's move on. Now remember one thing. I told you this point already, that it is very, sometimes you can think about Turing machine as a program, yes or no? You can think like this, that if a Turing machine can do, then your computer can do. If your computer can do, then Turing machine can do. So this type of thinking, sometimes it will help you. This type of thinking, sometimes it will help us sometimes, yes or no? Correct? So if a Turing machine can do, then program can do. If a program can do, then Turing machine can do. Okay, so basically this type of thinking, it will sometimes help you. Okay, now let's start the next topic. The next topic is all the concepts that we have seen. Can you apply those concepts? Okay, very simple. So take your copy pen, or maybe there is no need for copy pen, but just open your, just apply your ideas, just apply your concepts, just apply everything that you already know. Okay, so let's start. Now we will see the closure properties of decidable and Turing recognizable languages. So what we are going to see? We are going to see closure properties of decidable means REC. Decidable means recursive. Recursive means REC. And Turing recognizable means RE. Turing recognizable means RE. Okay, so now we will see closure properties of RE languages and recursive languages. Okay, and these are very, very, very easy. Okay, the proof we will see. All of them, the proof we will see. So let's start. Okay, so let's see the union operation. Let's see the union operation. So tell me, very simple questions I am asking you. Okay, closure under union operation. This is my question. Let's see this. Closure closure of recursive languages under union. Okay, so tell me what will be the question statement in this situation? What will be the question statement? What will be the statement? Tell me, just tell me the statement. What will be the statement? Statement will be, if L1 L2 are recursive, then can I say their union will be recursive? Yes or no? Basically the statement will be this. Statement will be this: if L1 L2 are recursive, if these are recursive, then L1 union L2 is recursive, then that is also recursive. Okay, so these are actually true. This is actually true. Recursive languages are closed under union operation. So I can say that, so this same statement I can say, so we can say that recursive languages are closed under, so I can say recursive languages are closed under, remember recursive languages are closed under union operation. Recursive languages are closed under union operation. Yes or no? So this is the point. Can you prove it? Can you prove it? This is true. This is true. Can you prove it? Can you prove it? So the proof is actually very simple. Okay, because remember L1 comma L2 are recursive, right? Yes or no? L1 is recursive, L2 is recursive. So what it means, just tell me this point. If L1 is recursive, L2 is recursive, what it means? It means there is a halting Turing machine M. There is a halting Turing machine M1 and there is a halting Turing machine M2. It will always halt or no? It will always halt or no? It will always halts. It will always halts. It will also always halts. Now, can we create halting Turing machine? Can we create halting Turing machine for L1 union L2? For L1 union L2, can we create that? Can we create halting Turing machine for L1 union L2? Yes, it is very easy. Yes, we can create halting Turing machine. We can create for L1 union L2. How will you create? Are very simple. This is very simple. So how will you create? Very simple. Because what you can do, you can create like this. You can create like this. So whatever W you take, what you will do? You will do like this. See, very simple. Whatever. Now this is how I am creating the Turing machine. So first of all, idea. Okay, let's see the idea. Idea is very simple, that whatever W you take, on input W, what you will do? On input W, you will run M1 on W. Okay, you will run M1 on W. Correct? Yes or no? You will run M1 on W. Will it halt? Will it halt? Tell me, will it halt? Will it halt? Will it halt? It will definitely halt. It will definitely halt because this is a halting Turing machine. So it will definitely halt. It will definitely halt. Yes or no? It will definitely halt. It will definitely halt. Then what you can do? If M1 accept W, if M1 accept W, then what you will do? If M1 accept W, okay, this is the idea. Okay, we are creating halting Turing machine M for L, M for L1 union L2. Remember, we are creating halting Turing machine for L1 union L2. So if you give a string W, what you do? You run this M1 on W. If M1 is accepting W, then what I can say? Then W belongs to LM. Then we accept W. Then M accept W. Yes or no? Then this M will accept W. Then I can say that. Correct or not? Is this clear? Then M will accept W. Very simple. So if M1 is accepting W, then then our Turing machine M will accept W. Okay. What is the second point? Else. Okay. Here, if M1 rejects, W, then what to do? If M1 rejects W, then what to do? Then you run M2 on W. Then you run M2 on W. Can I guarantee it will halt? Can I guarantee it will halt? It will definitely halt, because this M2 is also halting Turing machine. This M2 is also halting Turing machine. So it will definitely halt. Okay. So it will definitely halt. Now, if it accept, if M2 accept W, now, then if M2 accept W, then what you will do? Then also M accept W. Then also M accept W. Yes or no? Then also we are, okay, our Turing machine. We are creating a Turing machine for L1 union L2. We are creating a halting Turing machine for L1 union L2. Okay, so if M2 is accepting W, then also we will accept W. Else, finally, what will happen? Else M reject W. Else M will reject W. Yes or no? Else M will reject W. Is this clear to everyone? Please tell me. See, very simple. So very simple. You can create, if you have, okay, very simple. You can create halting Turing machine for L1 union L2. So like this, you can create. You can create halting Turing machine M for L1 union L2. How can you create? Very simple. Very simple. That if you take any string, then what you do? First you run M on W. First you run M1 on W. Okay. So whatever string is there on any input string, first you run M1 on W. If it accept, if it says yes, will I run on M2? If it says yes, will I run on M2? No, there is no need. So it will definitely halt. Yes or no? Do you agree it will definitely halt? Do you agree it will definitely halt? Yes, it will definitely halt. So when it halt and it says yes, then our Turing machine M, okay, what it will do? It will also accept. Then it will accept W. Okay. Now, then in this situation, M will accept W. Next, if it says no, okay, it will halt. And if it reject, basically, if it reject, here it is accepting. So if it reject, then what you do? If it reject, then you run W on M2. Then you run this W on M2. So then this W you will run on M2. Then you will give this W to M2. Okay. Now again, this M2, what it will do? Now, if this M2 says, this M2 will definitely halt. Yes, correct. This M2 will definitely halt. Okay, it will definitely halt. Now, if it says no, this M2 will definitely halt. And now I can say that it will definitely halt. Now, after halting, if it accept, okay, if it reject, either it will accept or it will reject. If it accept, then we will also accept. Okay, if it rejects, then we will also reject. This is your halting Turing machine for L1 union L2. Can you guarantee that this is halting Turing machine? Can you guarantee this is halting Turing machine? Can you guarantee this is halting Turing machine? Tell me, how can you guarantee? Can you guarantee this is halting? This machine is halting Turing machine. This machine. Look at this machine. Can I guarantee this machine is halting Turing machine? Yes, because M1 will definitely halt. Everything is halting. Okay, in this machine, you can notice everything is halting, correct? So you can guarantee that it is halting. So what we have done? So this machine is halting Turing machine. This machine is halting Turing machine. So what we have done? So L1 union L2 is recursive. Yes or no? So L1 union L2 is recursive. Agree or not? So what we have done? We have proven this. This proof we have done. So recursive languages are closed under union operation. This proof we have seen. Okay, this proof we have seen. Tell me, is this clear? The proof. Okay, so quite easy. Now let's see for RE languages. For RE languages, for recursive enumerable languages. So if they are RE languages, then their union is also RE. If they are RE languages, then their union is also RE. It means RE languages are closed under union operations. Okay, how can you prove it? RE languages are closed under union operation. But can we prove it? Can we prove it? So again, we can prove it. The proof is the proof is like this. So your L is RE, L1 is RE, your L2 is RE. What it means? Just tell me what it means. It means there is a Turing machine M, there is a Turing machine M1, and there is a Turing machine M2. Okay, there is a Turing machine M1, there is a Turing machine M2. Can we create Turing machine for? Okay, one more thing. Can I say this is always halts on strings in L1? Yes or no? This will always halt on W belonging to L1, and this is always halting on W belonging to L2. This always halt on W belonging to L2. Okay, very simple. Now, can you create a Turing machine? Can we create a Turing machine for? Can we create a Turing machine M for L1 union L2? Will this method work? Just tell me this method. Will this method work? Will this method work? Will it work? Will it work that this W run on M1? This W run on M1? Okay, will it work? Will it work that this W run on M1? If it says yes, then you also say yes. Then then final yes. Okay, if it says yes, then final yes. And if it says no, if it says no, then you run W on M2. Then you run W on M2. Will this work? Will this method work? Will this method work? Tell me why this method will not work. This method will not work. Correct? This method not work. This method will not work. Why? This method will it work? The answer is no. This method will not work. Why? Because this is a Turing machine. Because this is a Turing machine. So if W does not belong to M1, the problem, when the problem will happen? Tell me when the problem will happen. When the problem will happen. When the problem will happen, when? If, okay, the problem will happen if W does not belong to L1, but W belongs to L2. The problem will happen in this situation. See, please understand carefully. Problem will happen in this situation when W does not belong to L1, but W belongs to L2, and M1 loops on W. This is the problem. Agree or not? This is the problem. Agree or not? M loops on W. This string should be accepted or not? Finally, this string should be accepted or not by M. Finally, this string should be accepted or not? Finally, this string should be accepted or not? Yes, this should be accepted. This should be accepted because it is in L1 union L2. Finally, this string should be accepted. Finally, this string should be accepted by M. Okay, by M. Final, yes, by M. So this string should be accepted by M, but we are not able to accept it. Yes or no? But we are not able to accept it. Okay, so this method will not work. This method will not work. So can I say that we cannot create a Turing machine for L1 union L2? Can I say that these are not closed? No, because remember your Dovetteling, you can apply the Dovetteling. Okay, this is the analogy. This is the analogy. Very simple analogy. You know the analogy. There are two tunnels. There are two tunnels. The two tunnel analogy. Do you remember this two tunnel analogy? Okay, there are two tunnels. Basically, this is your M1 tunnel. This is your M2 tunnel. Okay, then what idea will work? Then definitely this idea will not work. Okay, that on W, you dig this. Okay, keep digging this. Keep digging this. Okay, keep digging this. So this idea will definitely not work. Agree or not? This idea will definitely not work. Okay, so this W, you keep digging. This idea will not work. But what idea will work? Very simple. Dovetailing will work. Dovetailing. This dovetailing will work. You can do dovetailing. What you can do? Again, okay. So you will do this one. Okay, 1 kilometer here, 1 kilometer here. Then 1 more kilometer here, 1 more kilometer here. 1 more kilometer, 1 more kilometer. 1 more kilometer, 1 more kilometer. 1 more kilometer, 1 more kilometer. If I do this, then tell me, if W belongs to, if at least one of them is finite, can I find it? If one tunnel is finite, can I find it? Now, if I do this, then I can definitely, if one tunnel finite, if one tunnel finite, if one tunnel is finite, we can find it. We can find it. Agree? Do you agree or not? Tell me. Okay. So this is the idea. Now, just give me a second. Hello. Is the audio clear? Tell me. So now, is the audio better now or previous? The audio is it better now or the previous audio was better? Tell me. Okay, previous. So okay. So let's do that. No problem. Okay. So now let's do. So basically now this will not work. So what we can do? We can do dovetailing. So what we are going to do? Remember, we are going to do this. So for how I'm going to create a Turing machine. So how will I create Turing machine M? So how will I create Turing machine M for L1 union L2? For L1 union L2, how will I create? Basically, whatever W you have, what you do, whatever W you have, you run this in dovetailing. Dovetailing on, okay, both of them. On both of them in parallel. Basically, that means dovetailing. That means dovetailing. It means what? It means dovetailing. Are we running in parallel or are we running in interleaving? Are we running in parallel or are we running in interleaving? We are running in interleaving. Okay, this is dovetailing. So when I create this diagram, remember this is my convention. Please understand. Please understand. This is my convention. This is my convention. If I create diagram like this, 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 what it means? Okay, if I create diagram like this, what it means? If I create diagram like this, it means I am doing interleaving. It means, it simply means I am running W. It means I am running W on M1, M2 using dovetailing in interleaving fashion. In interleaving fashion. Okay. So when I create diagram like this, it simply means that dovetailing. It simply means dovetailing method. Okay. It simply means dovetailing method. Is that clear? It means I am running in interleaving method. Is this clear? Parallel things are not possible. Mavit, I told you, you cannot do two things in parallel, right? Your computer can it do two things in parallel? Your computer, your processor, can it do two things in parallel? Can it run? Tell me, your processor, can it run? Can it run Google Chrome and your movie in parallel? Can it run Google Chrome and your movie in parallel? It looks like it is doing that. It looks like it is doing that, but it does not happen. Okay, it very fast it changes. Very fast it changes. Context switch happens very fast. Okay, context switch happens very fast. Is this clear? So two things are not happening in parallel. They are happening in interleaving fashion. Is this clear? two things are happening in interleaving fashion. Context switch is happening. Okay, so this is my convention. If I create diagram like this, does it mean parallel? Does it mean parallel? No, it does not mean parallel. It means I am running in dovetailing fashion. It means I am running in dovetailing fashion. Is this clear? I am running in interleaving fashion. So this diagram does not mean parallel. Please understand, this diagram does not mean parallel. This does not mean parallel. It simply means that this diagram simply means that I am using the dovetailing. So whenever I create diagram like this, it means I am using dovetailing. Okay, now you tell me. So what I will do, I will run this W on these Turing machines M1. This is a Turing machine M1, and this is your Turing machine M2. So I will run them in dovetailing fashion. Tell me. If it says yes, then what I will do? If it accept, then your Turing machine M, what it should do? Then your Turing machine M, what it should do? It should also accept, right? Then M accept W. Then M accept W. Okay. If it accept, then also your Turing machine will accept. Okay. Then also M will accept W. Now tell me. Okay. So, okay, is this clear? But remember, so can I say this is a Turing machine or halting Turing machine? Can it loop? This Turing machine, can it loop? It can loop, right? Okay. So what you can guarantee? One thing you can guarantee, tell me. One thing you can guarantee. What you can guarantee, tell me. One thing you can guarantee. So what I can guarantee? If W belongs to L1 union L2, if W belongs to L1 union L2, if W belongs to L1 union L2, what you can guarantee? Tell me. If W belongs to L1 union L2, if W belongs to L1 union L2, then either this will happen or this will happen. Either this will happen or this will happen. Guarantee? Yes or no? Either this will happen or this will happen. One of them will definitely happen. Either this will happen or this will happen. So either this will happen or this will happen. So can you notice that for members of L1 union L2, so for members of L1 union L2, can I say Turing machine M always halts and accept? Yes or no? Turing machine M always halts and accept. Turing machine M always halts and accepts. So what can I say about this Turing machine M? So what can I say about this Turing machine M? So I can say this is a Turing machine for L1 union L2. This is Turing machine for L1 union L2. So what can I say about L1 union L2? So this is Turing machine for L1 union L2. So what I can say? So we have created Turing machine for L1 union L2. So we have created Turing machine for L1 union L2. Okay, so we have created a Turing machine for L1 union L2. So this L1 union L2 is RE. Okay, so it is RE. Is this clear? This proof is this clear. Remember, what will happen if W does not belong to L1 union L2? Then if W does not belong to L1 union L2, now what will happen? If W does not belong to L1 union L2, if W does not belong to L1 union L2, then it may happen that M can loop. Then M may loop, may or may not. Okay, yes or no? Then what can happen? Then what can happen? Either it will reject or it will loop. Either it will reject or it will loop. So we cannot guarantee, right? Can I say we cannot guarantee for these, okay, for W does not belong into L1 union L2. This Turing machine M may or may not halt. May or may not halt. May or may not halt. Is this clear? So anyway, what we have created, did we create Turing machine or did we? So I can say So I can say, did we create Turing machine or did we create halting Turing machine? So did we create Turing machine or did we create halting Turing machine? So we have created Turing machine. So this is RE. So these two proof, are they crystal clear to everyone? These two proof, are they crystal clear to everyone? Tell me, please tell me. Crystal clear, not only clear, crystal clear. Like, did you understand everything? Please tell me. So what we have done? So this is the conclusion. So this is the conclusion. What is the conclusion? What is the conclusion? The conclusion is this. If L1 is recursive, union L2 is recursive, then the union also will be recursive. Then the union also will be recursive. So recursive, union recursive will be recursive. Is this clear? Similarly, if L1 is RE, union, if L2 is RE, then their then their union also will be RE. So union of RE will be RE. So this proof, the proof we have seen. You don't have to by heart. Basically, the proof we have seen. This is the conclusion. Okay. So RE union REC, sorry, REC union REC, that will be REC. RE union RE, that will be RE. What can you say about RE union REC? What can you say about RE union REC? Okay, so what can you guarantee it is REC? Can you guarantee it is REC? Can you guarantee it is REC? No. Okay, can I say RE, this is not REC? Can I say this union is not REC? Which statement is false? Some statements I am giving to you. Which statement is true? Which statement is false? So here, this statement is false. This statement is also false. This statement is true. Remember, because remember, this basically this may or may not be REC. Basically, this may or may not be REC. May not be REC. Can you give example? Can you give example? For example, I can give example. I can give give example for this. RE union REC is REC. Give example for this. Give example for this. Example is very simple. You can take ATM. You can take ATM. Acceptance problem of Turing machine. You can take ATM here, and you can take sigma star here, and you can take sigma star here. So this also will be sigma star. Yes or no? Next, you can take, and what is the counter example for this? Okay, can you give example for this? Can you give example for this? You can take ATM here, and you can take empty language here. So this also will be ATM. Clear? Tell me, yes or no? So quite simple. Is this clear? If you have this, if you have RE but not REC, if you have RE but not REC, let's assume a language is RE but not REC, and you union this with REC, what can you again say? What can you say? If you have RE but not REC, union REC, what can you say? Remember, you can say RE, that is fine, but it may or may not be REC. Again, it may or may not be REC. May not be REC. You can say it will be RE, but it may or may not be REC. The same, this example, if you notice, this is RE but not REC. The same example will work. The same example will work. Previous example. Okay, previous examples will work. Okay, is this clear? So this is very simple. So remember, this is false, this is false, this is true. So you can say why this is true, why this statement is true, because it is also REC. REC is also RE. REC is also RE. So because REC is also RE, so I can say that this will happen. Because REC is also RE, So I can say this will definitely happen. Okay. Now, so now let's see the intersection operation. Can you do, tell me, for this also, for the intersection also, what can I say? For the intersection, what I can say. So this is the idea. If you have, so this is the first thing, that is recursive or is decidable languages are closed under decidable languages are closed under are closed under intersection are closed under intersection. What it means, when I say this statement, when anyone says this statement, what this statement means, what this statement means, when anyone says this statement, what this statement means, this statement means that if you have a recursive language intersection with another recursive language, the result will be another recursive language. Recursive language intersection with recursive language, the result will be another recursive language. Can you prove it? Can you prove it? Can you prove? The same idea will work. The same proof will work. Okay, the same proof will work. What you can do? Because these are halting Turing machines. Remember, L1 is REC, L1 is REC, L2 is REC. So there is a halting Turing machine. So you know there is a halting Turing machine. So here also there is a halting Turing machine. So there is a halting Turing machine. Okay, so you know that this will always halt. You know this will always halt. And you know this will always halt. So tell me, can you create? Okay, now this is the question. Create halting Turing machine for L1 intersection L2. Okay, create halting Turing machine for L1 intersection L2. This halting Turing machine we have to create. Okay, so how will you create? Tell me, how will you create? Very simple. How will you create Turing machine, halting Turing machine for L1 union L2? The same idea you can do. Okay, very simple. So whatever W you give, so this is the halting Turing machine for L1 union L2. This is the halting Turing machine M for L1 intersection L2. Okay, what you will do, very simple. Whatever string W you have, run it on M1. Correct or not? Run it on M1. It will definitely halt. It will definitely halt. Okay, if it says no, if it says no, okay, if it reject, if it says no, then M will also reject W. Then M will also reject W. Yes or no? Then M will also reject W, because we are creating Turing machine for L1 intersection L2. We are creating Turing machine for L1 intersection L2. Okay, if it accept, then you run this W, on M2. Now you run this W on M2. It will also halt. It will also halt. Now if it accept, now you can accept. Now M will accept W. Yes or no? Now M will accept W. And if it reject, then M will reject W. Then M will reject W. Then M will reject W. Tell me, is this clear? So did we create halting Turing machine? Can I guarantee this Turing machine will always halt? Can I guarantee this Turing machine will always halt? Look at this Turing machine. Will it always halt? This Turing machine N will always halt. Yes. Okay, it will always halt. So what we have done? So this M is halting Turing machine. So this M is halting Turing machine for L1 intersection L2. So L1 intersection L2 is regular. That is recursive. So L1 intersection L2 is a recursive, because we have a halting Turing machine. Quite easy, these things. Now tell me, these proofs related to Turing machines, these are easy, right? In the last class, we have seen many proofs already. In the last class, in the reduction class, we have already seen many proofs. So the proofs related to Turing machines, these are really easy and interesting. Okay, so you can, so this is the idea. Now tell me, the second, What is the second? What can I say about recognizable languages? What can I say about recognizable languages? Are they closed? What can I say about recognizable languages? What can I say about recognizable languages? Recognizable languages. Yes, they are also closed. But will this method work? Will this method work? Will this method work? Tell me, will this method work? Actually, this method will work. Now this method will work. Now this method will work. Okay, now this method will work. See, this method will work. Now this method will work. You can check. Okay, just do it. Akash, Mavit, just do it. Take your copy and check it. Will this method work? Now that method will work. Do it. Just do it. Very simple. Very interesting things. Some interesting concepts. That method now will work actually. But you can use dovetailing also. Of course, yes or no? Of course, you can use dovetailing also. Okay, so proof number one. What is proof number one? The proof number one is very simple. This L1 is RE. This L2 is RE. Okay, the proof number one. L1 is RE, so there is a Turing machine M1. L2 is RE, so there is a Turing machine M2. Okay, now, you know this will always halt. Can I guarantee that it will always halt on W belonging to L1? And this will always halt. And this will always halt on W belonging to L2. Okay, so this is the idea. Okay, this is the idea. Now, create a Turing machine. Create a Turing machine for L1 intersection L2. Create a Turing machine for L1 intersection L2. Can you create that? Can you create that? Yes, we can create. Okay, the idea one. The proof one, or I can say idea number one. This will also work. See, dovetailing. The idea number one is your favorite. Your favorite dovetailing. Okay, dovetailing. Basically, what you do, very simple. Here, what you do, this is what you do. Okay, this is the idea number one. In the idea number one, what you do, whatever string is there, you run this on M1. You run this on M1. Whatever string is there, what you do, you run this on M1 also. And okay, when I create this diagram, what it means? When I create this diagram, what it means? When I create this diagram, it means dovetailing. It means dovetailing, interleaving execution. Interleaving running. Interleaving running. Okay, so this is your interleaving running. Now. So here, tell me. So you are running them. Okay, like one step here, 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 one step here. Like this, you are running. Yes or no? You are running one step, 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 one step. Okay, one step, one step, one step, one step. Like this, you are running. Okay, you are running like this. Now you are running them in the interleaving fashion. Now tell me, after this, okay, tell me. If it accept, if it accept, okay, let's assume if it accept, in this situation, when both of them accept, then in this situation I will accept W. In this situation I will accept W. Yes or no? In this situation I will accept W. So when both of them accept, then in this situation I will accept W. Is this clear? So what I will do, I will wait for both of them. Both of them must accept. Okay, this and this and this, then I will accept. Now tell me, can you guarantee for, okay, just tell me this point. Can you guarantee that for W belonging to L1 intersection L2, can you guarantee you will halt? Tell me. So this is Turing machine M for L1 intersection L2. So remember, this is your Turing machine M for L1 intersection L2. Can you guarantee for these strings? Okay, for these strings which are common, like these strings which are common, It will definitely happen. Yes or no? It will definitely happen. It will definitely happen. These two things will definitely happen. So it will definitely happen. So it will definitely happen. Yes or no? So I can say that. So this is a Turing machine. So I can say this is a. So what I can say? Tell me. So this Turing machine M definitely halt and accept. Definitely halt and accept on whom? Members of L1 intersection L2, right? Members of L1 intersection L2, correct? Members of L1 intersection L2. It will definitely halt and accept members of L1 intersection L2. This is your proof. This is your proof. Okay, so I can say for L1 intersection L2, there is a Turing machine. We have created a Turing machine. There is a Turing machine. So this L1 intersection L2 is a recursive. I is RE. So it is RE. Okay, so it is RE. Clear? This is your, but actually this method will also work. Can you notice this method will also work? The proof number 2. Actually, this method will also work. If you are creating Turing machine, M for L1 intersection L2, this method will also work. Which method? You give W. Okay. You give this W to M1. First you give this W to M1. Okay. If it accept, you give this W to M2. If it accept, then you give this W to M2. Okay. If it accept, then you give this W to M2. If it accept, then M accept W. Then M accept W. Okay. Then M accept W. No. Okay. Will this method work? Tell me, will this method work? Tell me, will this method work? Definitely this method will work. Can you notice? If I give W, if W belongs to L1 intersection L2, what will happen? If W belongs to L1 intersection L2, this will definitely happen or not? Just tell me. This will definitely happen or not? Okay. This will definitely happen or not? So this will definitely happen or not? Agree? Can you see? Tell me. Can you see? Very interesting. This proof, this method will work for intersection. For intersection, this method will work. For intersection, this will work. For intersection. Agree or not? Okay. Because yes, very good. Ekta, very good. Okay. What Ekta has written, that is very good. Because remember, whenever you are creating Turing machine for L1 intersection L2, okay, whenever you are creating Turing machine for L1 intersection L2, then what matters? Tell me what matters. What matters? Acceptance, halting and acceptance of members of that matters. Acceptance of W belonging to L1 intersection L2. Okay, acceptance of these strings matter. Correct? Yes or no? So can you see that if W belongs to L1 intersection L2, this will definitely happen. This will definitely happen. So this will definitely happen. So this proof will work. So this Turing machine will also work. So we have created two Turing machine basically. This, I can say, this Turing machine N also we have created. We have created Turing machine N also, and we have created Turing machine M also. Okay, so two Turing machine we have created for intersection. So this is Turing machine M. Okay, this is Turing machine M, and this is Turing machine N. Okay. So anyway, what we have done. So final conclusion. Tell me, what is the final conclusion? Tell me the final conclusion. What is that? The final conclusion is that if you have two recursive languages, okay, their intersection is recursive. If you have two recursive languages, their intersection is recursive. If you have two RE languages, their intersection is RE. Okay. The same thing you can also say for decidable. This same statement, I can say that Basically, this same statement, I can say that, basically, I can say that decidable intersection decidable. Decidable intersection decidable is decidable. And similarly, recognizable intersection recognizable. That is a recognizable. Okay. That is recognizable. So this is the conclusion. Is this clear to everyone? Tell me. So these things, they will improve your knowledge. The overall knowledge, they will improve. The overall knowledge of your Turing machine, halting Turing machine. Okay. Okay. So all these things, whenever you understand a proof, then what it does, like Nikhil is saying, whenever you understand a proof, then yes, your brain works. Okay. Your brain is working like very much. Okay. Your brain is working very, very, very much. So it improves your problem solving skills. That is important. Okay. So in Go classes, why we give any proof? Any proof, every proof we give, because it improves your problem solving skills. It will help you after gate exam also. After gate exam, if you go to IIT, IISc, PSU, or if you prepare for some other exam, if you prepare for TIFR, some complicated exam, GRE, whatever exam you prepare, CAT exam, MBA, if you do MBA, basically, okay, after learning in Go classes, after learning for 1 year in Go classes, one thing I can promise you, that your problem solving skills will improve very much. Then you can handle anything. Okay. Because this is very important. This problem solving skills, this is very important. People will say improve problem solving skills, improve problem solving skills, people will say. But we are doing that for 1 year, since we started. From that time, okay, till we will end, till the gate exam, okay, your problem solving skills will improve very much. Anyway, let's move on. So is this clear? Now let's see the concatenation operation. On this we will not spend much time, okay, because the proof is complicated for this. So for the concatenation operation, I will not spend much time, but I can give you the idea. The idea is very simple, that the idea is like this. Okay. So we will not spend much time, but the idea is non-determinism. Recursive concatenation recursive, recursive concatenation recursive, that is recursive. RE concatenation RE, that is RE. Tell me, can halting problem, can halting Turing machine, can halting Turing machine be non-deterministic? Can halting Turing machine be non-deterministic? Can halting Turing machine be non-deterministic? Yeah, no problem. No problem. Halting Turing machine means always halts. So it can be non-deterministic, no problem. Okay, it can be no problem. Yes, fine. Can it be non-deterministic? Yes, no problem. Ultimately, ultimately, this always halts. Okay, ultimately, this simply means always halts. Okay, ultimately, this simply means it always halts. So it can be non-deterministic. There is no problem. It can be non-deterministic. There is no problem. Is this clear? There is no problem. It can be non-deterministic. Okay. So now, so how will you create Turing machine for concatenation? If you have Turing machine for L1, if you have Turing machine for L2, how can you create Turing machine for L? Let's assume you have Turing machine for L1. For let's assume L1 is RE, and let's assume L2 is RE. Okay. So there is a Turing machine, right? So there is a Turing machine M1. There is a Turing machine M2. So there is a Turing machine M1. There is a Turing machine M2. Okay. So how can you create Turing machine for M1 unit? Now, create a Turing machine. Create a Turing machine for L1.L. How can I create Turing machine for L1.L? Okay. So how can I create Turing machine for L1.L2? So let me think. So one idea is to use non-determinism. See, actually, I'm thinking the idea suggested by some students. That is what I'm thinking. But one idea is very simple. The straightforward idea is very simple. That is use non-determinism. Okay. So how to create Turing machine for L1.L2? Whether it is RE or RDC, does not matter. So basically use non-determinism. See, this is the straightforward idea. Use non-determinism because there is non-determinism. Okay. So you have non-determinism. So you can use that. Okay. You can use non-determinism for to find out basically if L1 is RE and L2 is RE. These are two RE languages. Now, whatever string you give, you can use non-determinism to guess the partition. Is that clear? You can use non-determinism to guess partition. Basically, what I'm saying that this Turing machine M, we are creating Turing machine M for L1.L2. For L1.L2. Okay, what this Turing machine M will do? What this Turing machine N will do? On input M, sorry, on input W, what it will do? On input W, it will use non-determinism. Okay, it will use non-determinism. On input W, it will use, M uses non-determinism. M uses non-determinism to guess the partition, to guess the partition, to guess the partition, to guess the partition W dot W1 dot W2, where this comes from L1, where this comes from L2. Okay, where this is coming from L1 and this is coming from L2. So what you can do, your Turing machine M can use non-determinism to guess this partition. It can use non-determinism. Okay, we have already seen non-determinism in the PDA. In push down automata, we have already seen, okay, how to use non-determinism. Yes or no? In push down automata, we have already seen how to use non-determinism. So your Turing machine M can use non-determinism to guess the partition. Then what your Turing machine will do? Then very simple, then run W1, on M1. Okay, run W2 on M2. Okay, very simple. If both of them are accepting, then M will accept. Okay, yes or no? If both accept, then what you do? If both accept, then M accept W. Then M accept W. Is this clear? Then M accept W. So this is the idea. Anyway, we will not spend much time on this. So for concatenation, we will not spend much time because basically how to use this non-determinism, this is complicated. This can be complicated. Okay, how to use this, how to actually use non-determinism, that can be complicated. But this is the idea. Overall idea we have seen. Is this clear? In the books also, you will see only the idea. The idea is given. Only the idea will be given. Okay, so the same idea you can apply for, remember the same idea you can apply for recursive also. So if you have halting Turing machine, okay, for L1.L2, so the same idea you can apply. Remember what I'm saying? I am saying the same idea you can apply. If you have recursive, then there is a halting Turing machine, then how to create a halting Turing machine? Again, you can use non-determinism because halting Turing machine also can be non-determinism. No problem. This non-determinism is not a problem. Okay. Ultimately, this halting Turing machine must always halt. Okay. So you can notice for this, what will happen? Very simple. You can create halting Turing machine. The same idea you will apply. This M will not, you will use the non-determinism. This non-determinism you will use to guess the partition. Okay. You will guess this partition. Then very simple. Then you will run W1 on M1. Then you will run W2 on M2. If both, okay. Now, can you notice why you can guarantee that this is halting Turing machine? Tell me why you can guarantee this is halting Turing machine? Because it will definitely halt. It will definitely halt. Yes or no? Agree or not? Agree or not? See, it will definitely halt. It will definitely halt. So that is the reason you can guarantee that this is halting Turing machine. Okay. Yes or no? Because it will definitely halt. This thing and this thing. These things will definitely halt. Okay. So I can say, so finally we have created halting Turing machine. Anyway, this is enough. The idea is enough, right? Okay, is this clear? So this is the idea for concatenation. Now let's move on. The same idea for Kleene star. The same idea you can apply for Kleene star. So for Kleene star operation, the same idea as, okay, so for Kleene star operation, what you will do? For Kleene star operation, the same idea. Basically, if you have a RE language, its Kleene star will be RE. And if you have a recursive language, its Kleene star will be recursive. Okay, this idea will be same. Okay, the proof idea will be same. What is the proof idea? The proof idea will be same as concatenation, same as concatenation proof. Okay, same as concatenation proof. Basically use non-determinism. Basically use non-determinism. Okay, basically use non-determinism. Okay, what you will do here, actually two times you will need to use this non-determinism. You need to use two times. What are the two times? What are the two times? So actually for Kleene star, just think about a very simple point I'm asking. Let's assume this L is there. This L is there. W1, W2, W3, and so on. Tell me, when some string belongs to L star, what it means? This we have already seen. The basic idea. When some string belongs to W star, then what I can say? Then this W is, okay, then this W is basically, yes or no, K parts. Yes or no? Can I say? Then this W is basically K parts. Agree? Then this W is basically K strings. Or I can say K parts. Okay, where every part is a string from L, where every part belongs to 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 L. Agree? This is the definition of Kleene star. Yes or no? This is the basic definition of Kleene star. So basically understand the definition of Kleene star. We are understanding the definition of Kleene star. This we have already seen. Some questions also we have done. Understanding Kleene star. Okay, so you can notice that now this k is basically greater than equal to 0. This k is greater than equal to 0. So what you need to do, you need to first non-deterministically first you will guess this k. First you will guess this k. Okay, but guessing the k, is that enough? So tell me, if you have a string and I tell you there are k parts, is that enough? If I tell you there are k parts, is that enough? So what you, okay, remember, very simple. So first non-determinism. Okay, first non-determinism. First non-determinism, where, okay, what you will do? First non-determinism, you will use to, okay, used to guess number of parts. Okay, is this clear? For first non-determinism, used to guess in input W, used to guess number of parts in input W. Okay, so this, the first non-determinism you will use to guess the number of parts. Is this clear? You will use it to guess the number of parts, Tell me, is that enough? If you know the number of parts, then is that enough? In this W, if I know k parts, then what another we need? We need exactly which? Yes or no? We need what is the first part, what is the second part, what is the third part? Yes or no? This is not enough. We need what is the first part, what is the second part, what is the third part. This also we know. We need. So you know k parts. Now what you need? Now what we need? Tell me now what we need? Now what we need? Now we need the exact, like, okay, which is part. Basically now we need, now the second part is the second non-determinism. Now you will use the second non-determinism. The second non-determinism you will use to guess the parts, to guess those k parts, in W. Is this clear? To guess those k parts in W. Now we will guess those k parts. Okay, those, okay, those parts we will guess. So in this w, now we will guess those parts. Now we will guess those parts. Okay, is this clear? Now very simple. Now this is w1, this is w2, w3 and wk. Now very simple. Now what you do, now you run, okay, now you run w1. So okay, these k parts you will use. Now what you will do, now you run Turing machine m1 on w1, m1 on w2, m1 on w3, so on all of them. Is this clear? Because only one Turing machine we have, because we are, okay, remember this is the Kleene star operation we are thinking, because the Kleene star operation we are thinking. So basically if you have a RE language L1, if you have a RE language L1, then there is a Turing machine M1, right? Yes or no? Agree or not? There exists a Turing machine M1. Now we are creating Turing machine for, now we are creating Turing machine for, tell me, creating Turing machine for L1 star. Now, okay, so there is a Turing machine. For L1, there is a Turing machine M1. For L1, there is a Turing machine M1. Now we want to create a Turing machine for L1 star. We want to create Turing machine for L1 star. Okay, and for that we will use non-determinism. For that we will use non-determinism. Okay, is this clear? Tell me, is this proof clear? Like this idea, not the proof, but the idea. Is this idea clear? So for language L1, very simple. See, for language L1, there is Turing machine M1. Okay, so we have only one Turing machine. Now we want to create a Turing machine M for L1 star. Okay, so we will use non-determinism. So we will use two non-determinism. The first non-determinism to guess the number of parts. To guess the number of parts. What is the number of parts? Okay. Then the second non-determinism to guess the exact parts, to guess those k parts. Then what we will do? Then we will check. Then we will check. Basically, now what we will do? Now, okay, now what we will do? The third step. The third step. Now what we will do? Now we will check, does it belong to L1? Now we will check, does it belong to L1? Does it belong to L1? Okay, so for that, basically, for that we will run W1 on M1. We will run M1 on W1. We will run M1 on W2. Okay, and we will run M1 on WK. Okay, so this is the idea. Anyway, this is the idea, but I hope you got it. I hope you got it. But anyway, if you did not get it, anyway, this is the conclusion. This is the proof idea. Tell me, is this idea understood? Don't worry about the exact proof. Don't worry about how exactly Turing machine will do. Don't worry about that. Okay, Turing machine can do. Turing machine can do. We know. For example, Ekta, we know that Turing machine can compute logarithm. Yes or no? If you give any number, Turing machine can give you what is the logarithm. Okay, Turing machine can like if you give 100, then Turing machine can tell you what is the log 2 of 100. So, but how Turing machine will do that we did not see. That may be very complicated. Your program can do. If your program can do, Turing machine can also do. If you can write a program, then you can create a Turing machine also. If you can create a Turing machine, then you can write a program also. So whatever we have seen, okay, whatever we have seen, so this idea is enough. Okay, now anyway, now this idea, let me tell you, this idea is enough. Why I gave you this idea? Because once you understood this idea, then you will never forget this result. So this conclusion you will not forget. This conclusion you will not forget. What is the conclusion? That RE star, that is RE, and the same idea you can apply for REC star. REC star will be REC. Okay. Also RE dot RE, that is RE. RE dot RE is RE, and REC dot REC, that is REC. Remember, the same thing will work for Kleene plus also. The same thing will work for Kleene plus. So if you have Kleene plus, that also it will work. Okay, so RE recursive plus that is also recursive. Okay, so this is the conclusion. Now let's move on. Now interesting thing. Now the most interesting, that is complementation. The most important. Now we will spend time on this. The complementation. This is important. The fifth, that is complementation. Okay, this is very important. So let's see this last one. This is our last topic for today. That is complementation operation. You tell me one thing. RE languages, are they closed under complementation? Tell me. RE languages, RE complement. What can you say about RE complement? RE complement may or may not be RE. RE complement may or may not be RE. We have already seen some examples. Some examples we have already seen. For example, like, okay, yes, correct. Example number one. What was the example number one? For example, this is a sigma star is RE. Yes or no? This sigma star is RE, right? Language sigma star is RE. So this is your RE. What is the complement? What is the complement? The complement is also RE. So RE complement may be RE, right? RE complement may be RE. The second example. This emptiness problem, or maybe I can say that. Look at this problem. Finiteness problem. No. Look at this acceptance problem. ATM problem. Okay, ATM problem. That acceptance problem, that is RE but not REC. We have already seen. That is RE. Anyway, you know that is RE. RE but not REC. Okay, similarly, halting problem. And what is the complement of ATM? What is the complement of ATM? That is not RE. We have already seen all these things. That is not RE. Example, you can also take example number 3. Example number 3 you can take. Okay, let me take example number 3 like this. For example, you can say that consider this language. Okay, just consider this language. One language I am giving you. Just consider this language. L. Okay, L is set of Turing machines such that LM cardinality is greater than equal to 3. LM cardinality is greater than equal to 3. Okay, so tell me about this one. Tell me about this one. You can apply the Rice theorem. Apply the Rice theorem. So by Rice theorem and Dovetteling, by Rice theorem plus Dovetteling, by Rice plus Dovetteling. So what I can say? By Rice plus Dovetteling. What I can say? What is this language? Rice plus Dovetteling. Rice theorem is saying that this is non-trivial property. Okay, Rice theorem is saying this is non-trivial property. If you notice, this is a non-trivial property. Let's assume M is a Turing machine. M is Turing machine. So Rice theorem is saying that this is non-trivial property. So non-trivial property means L is not REC. L is not REC. Okay, non-trivial property means L is not REC. But this is monotonic property. So we use Dovetteling. So use Dovetteling. So in this situation, you use Dovetteling, right? Can Dovetteling help you? Yes, it can help. Because when you will stop, Dovetteling can help. When you will stop, okay, when you accept, when your counter reaches 3, when your counter will reach 3, as soon as you accept 3 string, you can stop. As soon as you accept 3 string, you can accept. So you can use Dovetteling. So this L is RE. We can recognize the members of L. We can recognize. So L is RE. So this language L is RE but not REC. What I can say? So this language RE, this is RE but not REC. What about complement of this L? So this L is RE but not REC. We know this is L is RE. Okay, we only care about RE. So this is RE. What about L complement? L complement means the cardinality is less than equal to 2. This is non-monotonic property. This is non-monotonic property. This is non-monotonic. This property is non-monotonic. So because this property is non-monotonic, so I can say this L complement. What can you say about this L complement? So L complement is not RE. So many examples we can have. Yes or no? Is this clear to everyone? So finally, I can say that RE complement, this language RE complement, it may or may not be RE. May or may not be RE. Agree? Okay. So what we can say? So RE languages are not closed under. So RE languages. So we can say RE languages are not closed under whom? Are not closed under in complementation. Complementation. Are not closed under complementation. Okay. So they are not closed under complementation. These RE languages. Okay. What about REC languages? What about recursive languages? What about recursive languages? They are closed. Okay. So let's prove it. Prove that complement of REC language, complement of recursive language is recursive. Prove that complement of recursive language is recursive. Recursive language is recursive. Complement of recursive language is recursive. This is what we need to prove. We need to prove that the complement of recursive language will be recursive. This is what we want to prove. Okay. This is extremely easy. Yes. So what you can do, this is very easy, very simple. You can create like this. You have, if you have L, if L is recursive, then what it means? Then what it means? Then it means there is a halting Turing machine M. There is a halting Turing machine M. It will always halt. Correct? It will always halt. Okay. So what this Turing machine M will do? What this Turing machine M will do? So what this halting Turing machine M will do? On W, it will halt and accept. It will accept. And I can say that on W, which do not belong to L, on W which do not belong to L, on them, what it will do? W which do not belong to L. It will reject. It will reject, right? It will reject. Okay. So what you do? Very simple. Okay. Just complement. Basically, now I am creating a, now this is the question. Okay. What is the question? The question is this. This is a question for you. So can you try this? Create halting Turing machine. Create halting Turing machine for L complement. Create halting Turing machine for L complement. Okay, create halting Turing machine for L complement. So this is what we need to create. We need to create what we need to create. We need to create what? We need to create halting Turing machine M dash for L complement. So what should happen? So what should happen here? So this M dash, what it should do? So this M dash, what it should do? It should do. This is the, okay, this is the objective. Okay, to create. This is the objective. What is the objective? Objective is this. So if you give W belonging to L, if you give W belonging to L, what it should do? What it should do? If you give W belonging to L, what it should do? It should reject. Okay, it should reject. And if you give if you give W not belonging to L, if you give W not belonging to L, then this should accept. This is our objective, right? This is our objective. Very simple. So very simple you can do. Now the proof number one. The proof number one, what is that? The proof number one is like this. So now you can create a Turing machine for L complement. This is your Turing machine M dash for L complement. So what you will do for any string W, what you will do? You will run this on M. Okay, what you do? You run this on, sorry, this is a halting Turing machine I'm creating. So halting Turing machine, you run this on M. It will definitely halt. Agree? It will definitely halt. Now, if after halting, if it says yes, if it accept, means if this M is accepting, then what we will do? Then what we will do? Then what this M dash will do? What this M dash will do? This M dash will reject. Okay, so here this M dash will reject W. And if here you reject, if this M is rejecting, then what your Turing machine will do? Then your M dash will accept. Then your M dash will accept it. Okay, yes or no? And the proof number 2 is very simple. The proof number 2. What is the proof number 2? The proof number 2 is very simple. For L, this is L is recursive. Okay, so there is a halting Turing machine. You know there is a halting Turing machine. Okay, so what to do in this? In this, if I change, if I make accept state reject, if I change this, if I make accept state reject, and if I make reject accept, if I do this change, if I do this change, if I do this change, accept state and reject state, if I do this change, then what will happen? Because you know the definition of Turing machine that we are considering. In our definition of Turing machine, what happens? In our definition of Turing machine, what happens? In our definition of Turing machine, what happens? There is a special accept state. There is a special accept state. There is a special accept state, and there is a special reject state. So there is a special accept state QACC, and there is a special reject state Q reject in our definition of Turing machine. So what you can say? So finally, what you can do this. If you do this, then you will get a halting Turing machine M dash, whose language will be L complement. Okay, whose language will be L complement. So this is REC. So this is a recursive. So this is your proof number 2. Okay. Can you notice one thing? Can you notice this proof will work if our definition of only for our definition of Turing machine? Yes or no? This proof will work only for our definition of Turing machine. Agree or not? Tell me. This proof will work only for our definition of Turing machine. But this proof number 1 will work for any definition of Turing machine. Yes or no? This proof number 1 will work for any definition of Turing machine. But the proof number 2 will work for our definition of Turing machine. So which proof is better? Both of them are correct. Both proofs are correct. But which proof is better? The proof number 1 is better, because that will work for any definition of Turing machine. Whatever definition of Turing machine you take, proof number 1 will work. But this proof number 2 will work for our definition of Turing machine. Okay? Is this clear? Anyone has any doubt in this? Tell me, is this clear to everyone? So remember, proof number 1, proof number 2, both are correct. Remember, okay, proof number 1, proof number 2, both are correct. This proof 1 and proof 2, both correct. Both correct. Both are correct. But this proof 2 works only, okay, but this proof 2 has a condition. But this proof 2 works only when, but this proof 2 works only when, works only when our definition of Turing machine considered. Our definition of Turing machine considered. Okay, this will work for any definition. Works for any definition of Turing machine. So in the interview, if they ask you which proof you will tell, in the interview, if they ask you, you can tell this proof, okay, then you can tell this proof. But remember, in the interview, you can also tell this proof also, but just mention that this is, sir, this is my Turing machine. This is my definition of Turing machine. If you want to say proof 2, then what you will mention? If you want to mention proof 2, then what you will mention? You will mention in the interview, sir, I am considering the definition of Turing machine in which there is a special accept state, there is a special reject state. Sir, that definition I am considering for Turing machine because that definition is given in the Sipser book. So the Sipser definition I am considering, Michael Sipser. Okay, that definition I am considering. Now, if I consider that definition of Turing machine, then this is the proof. Is this clear to everyone? Please tell me. Did you understand what I am saying? So the proof number 1 will always work for every definition. But if you want to give proof number 2, okay, if you want to give the proof number 2, then you should mention that that which definition of Turing machine you are considering. Then you can say that, sir, the Michael Sipser definition of Turing machine I am considering. Okay. Now, so that's very simple idea. So what we have done? We have done that recursive languages are closed under complementation. The recursive languages, they are closed under complementation. So this is very important conclusion. Anyway, conclusion I will give you after some time, but this is the idea. Recursive languages are closed under complementation. Now a very important theorem we will see. Let's see this theorem. What is the time? Okay, so we can finish this. Just very simple theorem, but it is very important. It is very simple, but it is very important. Okay, let's understand this. Let's understand this question. This is my question. Assume the L1 is RE. Sorry, assume L is RE. Assume L is RE. Okay, and L complement is RE. And L complement is RE. Then assume L is RE. L complement is also RE. Assume. Okay. Assume L is RE. L complement is also RE. Assume. Then prove that L is REC. Then prove that L is REC. Then prove that L is REC. Means if a language and its complement both are recursive enumerable, if you have Turing machine for language also and you have Turing machine for complement also, then that language is recursive. Then that language is recursive. Is this clear? Did you understand the statement? Did you understand the statement? What I'm saying? The statement, did you understand? Tell me the statement. So you can notice this is what we need to prove. We need to prove that if L and L complement, if both are RE languages, okay, then L will be recursive. So L complement will be recursive, yes or no? If L is recursive, so L complement automatically will be recursive. So L complement is also recursive. If L is recursive, then L complement is also recursive, yes or no? If L is recursive, so L complement also will be recursive. Is this clear? So we need to prove this. We need to prove that if L is RE and its complement is also RE, then we have to prove that L is actually recursive. This is what we need to prove. Okay, let's prove this. The proof is very simple. Okay, let's prove this. So this is what we need to prove. So if L is RE, then what it means, tell me. With this information, what you can say? With this information, there is a Turing machine. There is a Turing machine, right? So there is a Turing machine M1. Let's assume there is a Turing machine M1, or I can say there is a Turing machine M. Okay, L complement is RE. It means there is a Turing machine M dash. Here you have a Turing machine M, and here you have a Turing machine M dash, or I can say maybe M1 you can call it, and M2 you can call it. Is this clear? So this is the idea. Now this is okay. Create. Now what we will do? Now we will create. Tell me what we need to create. If I want to prove this, what I need to create? Tell me, if I want to prove this, what I need to create? I need to create halting Turing machine. Very good. So we will create halting Turing machine M for L. Okay, this is what we will create. Is this clear? We will create halting Turing machine M for L. Okay, how to create this? This is very simple. Again, very simple, very simple logic I will do. So I will create like this. This is how I will create the halting Turing machine for L. Halting Turing machine for L. Halting Turing machine M for L. What I will do, very simple, that whatever string you have, then for that string, what you do? Dovetailing, use dovetailing. Use dovetailing. You run this on M1 also. You run this on M2 also. You run this on M1 also. You run this on M2 also. Is this clear? Tell me. Dovetailing. Use the dovetailing. So you run this on this W. You run this W on M1 also. You run this on M2 also. Okay. Use dovetailing. Here I'm using the dovetailing method. Okay. Means one step here, 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 one step here. Okay. So like this I'm running. Very simple. So I will run this M1 on W for one step. Then I will run this M2 on W for one step. Then one step. Then one step. One step. Sorry. One step. One step. One step. One step. One step. One step. Like this I will do. So this is my dovetailing method I am using. Okay. Now tell me. Tell me. Can you notice very interesting thing? Here the language is L. Yes or no? Here the language is L. And here the language is L complement. Here the language is L. And here the language is L complement. So, okay. So what you can guarantee? Just tell me. Okay. Before that. Okay. Let's create this. So if it accept, if this L is accepting, then I am creating Turing machine for L. I am creating Turing machine for L. So if it accept, if L is accepting, means if L is containing W, so what should I do? So what should I do? Tell me. So here, what should I do? Remember, I want to create Turing machine, halting Turing machine for L. So in this situation, what should I do? I should accept, because if M1 is accepting, then it means W belongs to L. If W belongs to L, then I should also accept. Yes or no? Then M will also accept W. Okay. 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 If this accept, then what we should do? If this accept, then what we should do? Then we should reject. Yes or no? Then we should reject W. Okay, very simple. Because if this will accept, it means W is in L complement. It means W does not belong to L. So if this accept, then we will reject W. Okay, very simple. Now, can you notice? That's it. Now, my claim, this machine that we have created, I guarantee that this is halting Turing machine. This machine that we have created, I guarantee that this is halting Turing machine. How can I guarantee that this is halting Turing machine? This machine that we have created, prove that this is halting Turing machine. Now, our task, what is the task? Prove this Turing, this machine that you have created is halting Turing machine. Prove it. Prove this machine that this is halting Turing machine. So what we will do, very simple. You can notice that if W belongs to L, can I guarantee I will halt? Can I guarantee I will halt? If W belongs to L, can I guarantee I will halt? For these, can I guarantee I will halt? For these, definitely this will happen. Agree or not? For these, definitely this will happen. Yes or no? Are definitely this will happen. So definitely this will happen. Okay, yes or no? Definitely this will happen. So for these, I can say for W belonging to L, M definitely halts. And accepts. Agree? Very simple. Okay. Now tell me, is this enough to prove that this is halting Turing machine? Is this enough? Okay. So we need to prove this. We need to prove that this M is halting Turing machine. We need to prove this. Okay. So you can notice that what we have done. So here we have done that if W belongs to L, then M will definitely halt and accept. Is this enough to say that this is halting Turing machine? Is this enough to say that this is halting Turing machine? Is this enough? This is not enough. For non-member also you must halt. Okay, so if you give a non-member, then what will happen? So if you give W does not belonging to L, if you give W does not belonging to L, then what will happen? If you give W does not belonging to L, then definitely this will happen. Agree or not? Then definitely this will happen. Definitely this will happen. So definitely this will happen. So definitely this will happen. So I can say what I can say. So for W, so for W does not belonging to L, this Turing machine M definitely halts and rejects. Agree? Definitely halts and rejects. Is this clear? Tell me. So definitely it will halt and reject. So what we have done? So this is halting Turing machine. So this is a halting Turing machine. Is this clear? So this is what we have done. So we have now we can say it is halting Turing machine. So this is done. So okay, whatever W you give, so this M is halting Turing machine for L. So L is a REC. So L is recursive. Tell me, is this proof clear to everyone? Is this crystal clear to everyone? Okay, is this clear? Very simple, right? All these proof in this lecture, in today's lecture, every proof that we have seen, all the proof. Did you understand all the proof? Tell me, every proof. And this is also very similar. So you can guarantee that. So you have created halting Turing machine. So, okay, this is the conclusion. So what is the conclusion? The conclusion is this. If L comma L complement both RE, if L complement both RE, then L comma L complement are both REC. Yes or no? Is this clear? Then actually they are both REC. And this is if and only if statement. If they both are REC, then can I say both are RE? If both are REC, can I say both are RE? If both are recursive, can I say both are RE? So this is if and only if statement. This is a if and only if statement. This is if and only if statement. So if both are REC, then both are RE. If both are RE, then both are REC. Because every recursive language is RE. Every recursive language is RE. And if L and L complement both are RE, then they both are recursive. Okay, and this is many interesting consequences are there. This theorem has many interesting consequences. Okay, many consequences. This result, remember, this theorem has many consequences. This is very important theorem. I will tell you what are the consequences. What is the important theorem? That if I can say L comma L complement both RE, if and only if, okay, if both are RE, then what will happen? If they both are RE, then both are recursive. Both recursive. Then they both are recursive. Okay, and this theorem has many consequences. This theorem has many consequences. Many consequences. Let's see one by one, all of them. So these are the many consequences. So tell me, is it possible? Is it possible? Consequences means many results, many further results you can say. Many further results you can say. Many further results. Many further results you can say. Okay. So what are the further results? So very simple point. Just tell me this point. Is it possible? Is it possible? Is it possible? This is the question. Okay. See the question. Now the question is it possible? The question is it possible? Okay. So this is the question. Now let's see. So I am giving you, let's assume this is the set of recursive languages. This is the set of recursive languages. This is the set of RE languages. This is the set of RE languages. And let's assume this is all the languages. And let's assume this is all the languages. And let's assume this is all the languages. Okay, this is all language. Okay, so this is all languages. Now, okay, very simple. So tell me, is it possible? Some question I am asking one by one. Is it possible that L can be here and L complement can be here? Is it possible? Is it possible L can be here, L complement can be here? Is it possible? Yes. Because if L is here, then L complement will be here. Of course, yes or no? Because you know that recursive complement is recursive. You already know recursive complement. Recursive complement is recursive. You already know. It means decidable complement is decidable. If your problem is decidable, if your language is decidable, its complement also will be decidable. Correct? Okay. Now tell me, so is it possible that L can be here? L can be here and L complement is here. Is it possible? Is it possible? Means L complement is RE but not REC. Why this is not possible? Never. Is it possible? No. Never. Is it possible? No. Never. Why? Because if L is recursive, then L complement will be recursive. Yes or no? If L is recursive, then L complement will be recursive. Because if L is recursive, then L complement will be recursive. Okay. Tell me, is these two statements are the same? Like, okay, if L is RE, if L is recursive, can I say L complement can be RE? Can I say if L is recursive, can I say L complement will be RE? Yes. But what this statement is saying, then what this diagram is saying? Tell me what this diagram is saying. Remember, if L is recursive, then L complement will be recursive because L complement is REC. Because L complement will be recursive and recursive is RE. So what this diagram is saying then? Then tell me what this diagram is saying. This diagram is saying that if L is recursive, then L complement is RE but not REC. Okay. If L is recursive, then L complement is RE but not REC. L complement is RE but not REC. This is never possible. If L is L complement, then L. Okay, so this thing is never possible. This thing is never possible. Is this clear? This thing is never possible. Okay, now tell me about this one. Is it possible that L is here and L complement is not RE? It means not RE, right? It means not RE. Is it possible? Is it possible? Again, no. Not possible. Never. Again, the same logic. Because if L is recursive, then L complement will be recursive. Again, the same logic. If L is recursive, the same logic. If L is recursive, then L complement will be recursive. Okay. So what is the next? Tell me, is it possible that L is here and L complement is here? L is here, L complement is here. Is it possible? This is the consequence. This is no, never. Because I told you if both are RE, then both are recursive. Yes or no? This is the result. Please understand the result. If both are RE, then actually both are recursive. The only possibility that both can be RE is when both are recursive. Yes or no? Remember? So note. So the only possibility, the only way, okay, remember the only way, okay, both L comma L complement can be RE is when both are RE, when both are REC, is when both are REC. Okay, the only possibility they can be RE, the only possibility, the only way they both can be RE, that is when both are REC. Yes or no? This is the theorem. This is the theorem we have proven. We have already proven that if both are RE, then they are REC. This is what we have proven. Yes or no? This is what we have proven. The proof we have seen. The proof we have seen that if L and L complement both are RE, then they both are recursive. So the only way they can be RE, L and L complement, the only way they can be RE is when they are recursive. So tell me, is this possible? L and L complement are here. This is not possible. Why this is not possible? Because if L comma L complement are RE, if both are RE, then they must be recursive. Then they must be here. Then actually they must be here. Tell me, is this clear or not? Is this clear or not? So I can say this is never possible. Means L is RE but not REC. L is RE but not REC. And L complement is RE but not REC. This is never possible. This is never possible. Okay, and when this is possible, that this is RE and this is RE. When this is possible, this is possible. This is possible. When this is possible, this is possible only when. This is possible only when. This is possible only when. This is possible only when L comma L complement are REC. Or I can say L is REC. Okay, or this is enough, right? If I say L is recursive, this is enough. Automatically L complement will be recursive. Automatically L complement will be recursive. So this is what I'm saying. So this is possible. L and L complement both are RE. This is possible only when L is recursive. Okay. So one very interesting result is here. One very interesting result is coming. If L is here, where is L complement? If L is here, where is L complement? If L is here, where is L complement? What is L complement? If L is here, what is L complement? Can L complement be here? One by one. One by one. Where is L complement? This is the question. This is the question. Can L complement be here? Can L complement be here? No. Because if L complement is here, then what will be the problem? Then what will be the problem? Then L will be here. Then L will be here. Can L complement be here? Can L complement be here? Again, no. Again, no. So finally, L complement must be here. So what is RE? So what is L complement? L complement must be not RE. L complement must be not RE. Yes or no? Is this clear? So what is the result? The very important result that if your language is RE but not REC, if your language is RE but not REC, then its complement will be not RE. Then its complement will be not RE. And this result is very, very important. Why this result is very important? Because Rice theorem, when you apply the Rice theorem, once you get this result, then L complement is not RE. Is this clear? So RE but not REC complement will be not RE. Okay, it will be not RE. So I can say this is very important. This result is very important. Okay, next. So you why this result is important? Let me tell you. For example, ATM. You know ATM, HPTM, halting problem of Turing machines, ATM, HPTM, state entry problem. You know state entry problem of Turing machines. Okay, these things, state entry, the blank tape problem of Turing machines, blank tape problem of Turing machines. So all these, okay, ATM, HPTM, this state entry problem of Turing machine, blank tape problem of Turing machine. This is your state entry problem. This is your state entry problem. Okay, and this is your blank tape problem. This is your blank tape problem. We have already seen that these are RE but not REC. We have already seen these are what? We have already seen these are RE but not REC. All of them are RE but not REC. Correct? So what I can say now? So I can say that their complement, ATM complement, HPTM complement, SEPTM complement, blank tape of Turing machine complement, these are not RE. All these will be not RE. All these will be not RE. So this theorem is important. Yes or no? Is this clear to everyone? Okay. So very simple. Now another thing, is it possible that L is here, L complement is here? Is it possible L is here, L complement is here? Is it possible? This is blank tape problem. This is blank tape problem of Turing machines. This we have already seen in the lectures. In the previous lectures, we have already seen what is blank tape problem. BTTM, blank tape problem. We have already seen this, right? Mavit, do you remember this? Blank tape problem we have already seen. Okay. Now, so this is blank tape problem of Turing machine. Now tell me here, is it possible that both are not RE? Is it possible both are not RE? Is it possible both are not RE? This is possible. Many examples we have already seen. This is possible. This is possible. Many examples we have already seen. Many examples we have already seen. For example, this L, finiteness problem. Finiteness problem of Turing machines. Finiteness problem of Turing machine. Infiniteness problem of Turing machine. Both are not RE. Yes, agree or not? Finiteness problem of Turing machine. Both are not RE. Correct? Yes or no? Is this clear? Like finiteness problem of Turing machine. Why this is not RE? Tell me why this is not RE. Why this is not RE? Why this is not RE? Because this is non-monotonic property. Rice theorem. Rice theorem, Rice theorem, Rice theorem. Because this is non-monotonic property. So this is not RE because this is non-monotonic property. Because this is non-monotonic property. So you can say that this is a not RE. So I can say this is not RE. Okay, so I can say this will be not RE. And you can notice why this is not RE. Why this is not RE? Why this is not RE? Because dovetailing cannot help. Because dovetailing cannot help. This is not RE. Dovetailing cannot help. Dovetailing cannot help. This is what I'm saying. Is it possible? See, Nikhil, sorry, Mavit, I am saying, is it possible? See, read the question. I am asking, is it possible? I am asking the question, is it possible? Please understand this. I am asking, is it possible? Is it possible both are not RE? Is it possible both are not RE? Yes, it is possible. It is possible, right? For example, this example you can take. Many more examples you can take. Many more examples. For example, okay, this example you have like finiteness problem and infiniteness problem. Both are not RE. For example, consider this problem. Regularity problem of Turing machine. Consider the regularity problem of Turing machine. What is that? Regularity problem of Turing machine. M is TM. M is Turing machine. LM is regular. LM is regular. What will be L complement? Tell me what will be L complement? What will be L complement? L complement will be M is Turing machine. LM is not regular. LM is not regular. Can you notice both are non-monotonic? Can you notice both are non-monotonic property? This is also non-monotonic. This is also non-monotonic. We have already seen. This is also non-monotonic. This is also non-monotonic. This is also non-monotonic. This is also non-monotonic. Both are non-monotonic. Okay, so both are non-monotonic. So I can say that L here L is not RE. So I can say here L is not RE, and here L complement is not RE. So both can be not RE. Is this clear? So both can be not RE. So here also both are not RE. So this is the question. Is it possible? This was the question. Our question was, is it possible? Yes, possible. Possible, right? Yes or no? So this is possible. So remember, please understand this. Please understand that not RE complement. Not RE complement. Where it will go? Where it will go? Not RE complement. Either it will be not RE, either it will be not RE, or it will be RE but not REC, or it will be RE but not REC. Clear? Let me know. Is this clear? Tell me. Not RE complement can be not RE, or it can be RE but not REC. Either it will be not RE, or it will be RE but not REC. What about RE but not REC complement? What about RE but not REC complement? RE but not REC complement. That will be not RE. That will be not RE. Clear? Tell me all these points, are they clear? I told you so many consequences. I told you so many consequences. So can you see these consequences? Can you see? Okay. Is it possible that one is here, one is here? Is it possible? One is here, one is here. It is possible. Yes, it is possible. Okay, one is here, one is here. Is it possible this is here, this is here? Of course. Okay, so all these things are possible. So these are definitely possible. Okay, tell me. If L is here, then where is L complement? What is L complement? Now the question is, what is L complement? Now the question is, what is L complement? Okay, so if your L is here, then what is L complement? Tell me. Is it possible questions we have seen? Now let's see what is L complement questions. So what is L complement if your L is here? So if your L is here, then definitely your L complement will be either not RE, either your L complement will be here, or it will be RE but not REC. Or it will be RE but not REC. So remember, either your will be here, L complement, or your L complement will be here. So either L complement will be here, either L complement will be here, or L complement will be here. So I can say where your L complement will be, where your L complement will be either this or this or this. Okay, so either this or this. Did you get it? Either this or this. Okay, so either it will be not RE or so. Tell me the next. If your L is here, if your L complement is here, then where is L? If your L complement is here, where is L? The same answer. The same answer. Either your L will be here or your L will be here. And it is, this is just to confuse you. This is just to confuse you. L complement. This is just to confuse you. You can call it J, then it will become J complement. This is just to confuse you. Is this clear? Is this clear to everyone? If you call it J, it will become J complement. Okay. Next, what about this one? If your L is here, where is L complement? If your L is here, what is L complement? That will be recursive. That will be recursive. Okay. So quite simple. And if your L is here, if your L is here, what is L complement? That will be not RE. That will be not RE. And if you're okay, so anyway, so all the variations we have seen, right? Agree? Okay, so all the variations, every variation we have seen. So from my side, every variation and everything we have seen. Not RE complement can be recursive. Not RE complement. If L is not RE, if L is not RE, can L complement be recursive? If L is not RE, can L complement be recursive? No. If L complement is recursive, or if L complement is recursive, then what will happen? If L complement is recursive, if L complement is recursive, then L will be recursive. Then L will be recursive. You know L complement whole complement is, L complement whole complement is L. This is just to confuse. L complement. If you call it J, then it will become J complement. You also know L complement whole complement. L complement whole complement will be L. So any language recursive complement will be recursive. Okay. So like this. Anyone has any other doubt? Any other doubt, anyone? Please tell me. So this is your chapter. Okay. We have seen all the things. All these. So, okay, all these things we have seen. Everything we have seen. All the things. So finally, this is your, okay. So what we have done, this is your closure property table. But in this property, in this table, almost all the proof we have seen. You don't have to by heart this table. There is no need to by heart this table because all the standard operations, all these standard operations proof we have seen. Yes or no? For all the standard operations, the proof we have already seen. For all the standard operations, for all these standard operations, all of them, these proof we have seen, these proof we have seen, these proof we have seen. Basically, almost all the proof we have seen. If you check, okay. So in this table, almost everything we have seen. So this is your table. You can just check it out. RE languages are not closed under complementation. This is the only thing. See, if you notice, the RE languages, they are not closed under complementation. They are not closed under complementation. Also, you know, context-free languages are not closed under complementation. Okay, we have already seen this proof. We have seen that complement of regular language is regular. This proof we have seen. And what was the important point in this proof? This is most important point. Remember? Okay, in this proof, what was the most important? The DCFL complement is DCFL. DCFL complement is DCFL. In this proof, what was the most important point? I told you. In this proof, what was the most important point? In the proof idea. In the proof idea, what was the most important point? Important point, what was that? Anyone remembers? Important point. Important point was this, that for every DPDA, you can create another DPDA which will always read the string. This was the important point. DCFL complement I am talking about. Nikhil, I am talking about DCFL complement. From where are you getting the non-determinism? I am talking about DCFL complement. In the proof, what was the important point? Anyone remembers it? What was the important point? Anyone? The important point was that for every DPDA, okay, for every DPDA M, we can create another DPDA which will always read the string, which will always read the complete entire string. For every DPDA M, we can create another DPDA M2 which will always read the entire string. Which will always read the entire string. Always read entire string. So basically, in what is this proof? Let me tell you the idea. DCFL complement. This is DCFL. Okay, the proof idea, let me tell you. Okay, so let me tell you the proof idea. So let's see the proof idea. Basically, if you have a DCFL, then there is a DPDA, right? If you have a DCFL, then there is a DPDA, correct? If you have a DCFL, then there is a DPDA. Okay, now tell me, this DPDA, tell me, this DPDA, can I say it will always read the entire string? Can I say it will always read the entire string? See, the strings which are in the language, those will be read entirely. Okay, see this DPDM, if you notice this DPDM, W belonging to L, then W will be read entirely. Yes or no? In this situation, you will read W entirely. In this situation, you will read W entirely. In this situation, M will read entirely W. In this situation, M reads W entirely. Entirely. In this situation, you will read W entirely. But if W does not belong to L, I can also reject if there is no move. If there is no move, I can reject. Are yes or no? If W does not belong to L, if W does not belong to L, this DPDA can reject without reading the entire string. Agree or not? Agree or not? This DPDA can reject without reading the entire string. For example, if there is no move, let's assume here there is no move. Let's assume if there is no move, if there is no transition, then this DPDA can reject without reading the entire string. Agree or not? Agree or not? So if W does not belong to L, then M may not read W entirely. Agree? Do you agree? Tell me this point. Because maybe if W does not belong to L, if W does not belong to L, then maybe this M can reject here if there is no move. If there is no move, then M rejects. Correct or not? Tell me. If there is no move, then M will reject. So M may not read entire W. Now, the idea is very simple. What you do, from this DPDA, you can create another DPDA. From this DPDA, you can create another DPDA, which will always read the entire string. Is this clear? From this DPDA, you can create another DPDA, okay, convert. From this DPDA, you convert into another DPDA, which always read entire string. Which always read entire string. Which always read entire string. Okay. Now, in this DPDA, you can change the accept and final state. Okay. In this DPDA M2, in M2, you can change the final and non-final state. You can change the final and non-final state. In this DPDA, you can change the final and non-final state. Okay. In this DPDA M2, you can change the non-final final state. Then L complement DPDA you will get. Then L complement DPDA. Then you will get a DPDA. Then you will get a DPDA M3. Okay, you will get a DPDA M3, which will accept M3, which will accept L comp. Okay, so this is the complete idea. Anyway, so this is the complete idea. Is this idea clear? Tell me, is this idea clear? What is happening here? Tell me. Very simple. DCFL complement is DCFL. DCFL complement is DCFL. And what is the idea of the proof? The idea of the proof is like this. See, if you have a DCFL, then there is a DPDA. But there is a DPDA. Now, this DPDA will read the entire string. If W belongs to L, then DPDA will read the entire string. But if W does not belong to L, then M may not read the entire string. Because if there is no move, then this DPDA will reject the string. If there is no move, then DPDA will reject the string. So now what we do, the proof idea is this. From this DPDA, you convert this to another DPDA. You convert this DPDA to another DPDA, which will always read the entire string. Okay, so you convert this to another DPDA, which will always read the entire string. Then in this DPDA M2, what I'm saying, in this DPDA M2, what you do? In this DPDA M2, you do this. Final, non-final, you exchange. Then you will get another DPDA which will accept L complement. Okay. So this is your complete. So you can notice this is important. If you notice, for complement, DCFLs are, this is important. DCFL complement is DCFL. DCFL complement is DCFL. So these things are some important things. Okay. Anyway, so only standard operations are important. These standard operations, these are important. The remaining you can by heart. The proof of this is important. In any interview, if they will ask you proof, then they will ask you here. Okay. In any interview, if they will ask you proof, they will ask you here. They will ask you for the standard resources, for the standard operations. Okay. This screenshot is taken from gateoverflow website, from gate CSE website. There is a gate CSE website. You can check it out. Okay. So this screenshot is taken from gate CSE website. You can Google it. This is a website of Gate Overflow. This is a website of Gate Overflow, gatecse.in. This is a website of Gate Overflow. So this is a Gate Overflow website. Okay. Any other doubt? Did you understand everything? Please tell me. Any other doubt, anyone? Any other doubt? So far in this lecture, whatever we saw, in this lecture, every point did you understand? Every point, every single point did you understand? Let me know if anyone has any doubt. Anyone has any doubt, let me know. Yes, Arnab. Arnab,
Good
what is the
evening, sir.
doubt?
Yes, sir. I am asking you that
Hello,
there is
Arnab.
a no, no. Hello, am I audible?
Are you speaking?
Hello, am I audible?
Okay. Mm,
Same problem. Okay.
just wait. Please tell me what is the doubt?
Hello, am I audible?
Yes, yes, you are audible.
Okay. So, in good evening, sir. In the in the in the in the part that not R is complement, not R complement. In
Mm-hmm.
the slide you explained that not RE complement is not RE, I understood. But for the another part that not RE complement is recursively enumerable but not REC. This is my doubt. That that thing I didn't
So
got it.
take this language. Take this language. I got your doubt. So let me explain. Okay. You
Okay,
can
sir.
you can unmute. You can mute yourself.
Okay, sir. Okay, sir. Mute.
So you take this language. Like consider this language L. L is M is regular. Sorry. Consider this language L. M Turing machine. M is a Turing machine. M is a Turing machine. And LM cardinality is greater than is a less than equal to 1. Okay, is less than equal to or 2 or whatever. Okay, so you see this. Tell me, is this language L? Is this not RE? Is this language not RE? This is non-monotonic property, right? Okay, so this property is non-monotonic. This property is non-monotonic. This property is non-monotonic. So because of this property is non-monotonic, so this language is not RE. So this language L is not RE. What is L complement? Arnav, can you tell me what is L complement? Just tell me what is L complement. Just tell me what is L complement. This L is not RE. This L is not RE. Just tell me what about L complement. Arnav. Arnav, what is L complement? Tell me. Set of Turing machine where M is a Turing machine such that cardinality of LM is greater than or equal to 3. This is RE, right? Yes or no? This language is RE but not REC. Dovetailing can help you. This is RE but not REC. Who will help you? Dovetailing. Who will help you? Dovetailing. Using dovetailing. Use dovetailing. Use dovetailing. Okay. As soon as you accept 3 strings, you can stop. Is this clear to everyone? Please tell me. So you can notice that if you have not RE, if your language is not RE, if you have a not REL, if your language is not RE, then L complement may or may not be. So L complement can be not RE, L complement can be not RE, or L complement can be RE but not REC. RE but not REC. But it can never be REC. It can never be REC. So either it will be not RE or it will be RE but not REC. But it can never be REC. This L complement can never be REC. Can never be REC. Okay. Anyone has any other doubt? So this is clear. Okay. Arnav was asking this doubt. This is also clear. Anyone has any other doubt? Yuvraj, Nikhil, Mavit, Kusal, Ekta, Astos, Alap, Akash. Any other doubt? KS. Okay. So this is enough. Now you can join the after half an hour, you can join operating system class. Okay, not half an hour. Yeah, I think half an hour. Okay, it will start at 8, right? 8 p.m. So after 40 minutes, you can join operating system class. Okay. 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 Thank you, everyone. So this is your lecture. Tomorrow in the morning, we have dbms class. In the morning, 7 a.m. the same time, 7 a.m. That is a fixed time. Morning class dbms, that will be fixed. Today was Sunday, and there were some students who told me to, actually I wanted to take at 7, but then some students told me to take at 11. Then I also got lazy. Okay, so anyway, so tomorrow we will start at 7 a.m. Okay, in the morning tomorrow dbms 7 a.m. Okay, thank you.